What if every star that twinkles in the night sky and every planet orbiting those distant suns is not simply a random dot or celestial body, but rather a faint, lingering whisper from an ancient, vast past that stretches far beyond our imagination? The universe, teeming with unfathomable complexities and mysteries, began with an event so extraordinary that its echoes still resonate through the cosmos today. This event was so monumental, so beyond the grasp of ordinary comprehension, that it shaped everything we know about existence itself. Are we now standing on the precipice of a monumental breakthrough, ready to finally unravel the profound question that has captivated humanity for millennia? Where did all particles, the fundamental building blocks of everything, truly come from? The story of the universe's origin, as understood by modern science, begins with the Big Bang Theory. This theory presents the universe as emerging from an unimaginably hot and dense state, a singular point so compact that it defied all conventional scales of size and matter. Picture the entire cosmos, galaxies, stars, planets, and all the matter in between, compressed into a space smaller than the tiniest grain of sand. Around 14 billion years ago, this minuscule but intensely packed point began to expand, marking the birth of everything. It is crucial to understand that this was not an explosion happening somewhere in space, but rather the expansion of space itself, stretching and growing at a phenomenal pace, carrying all matter and energy outward in every direction. As the universe stretched and grew larger, it began to cool down, allowing the fundamental particles to coalesce into protons, neutrons, and electrons. These particles, dancing in a primordial cosmic soup, eventually joined forces to form the simplest atoms. Hydrogen and helium, the two lightest and most abundant elements, emerged first. These atoms gathered into massive clouds that, under the pull of gravity, collapsed and gave birth to the first stars and galaxies. This narrative forms the backbone of the Big Bang Theory, a theory that holds immense weight because of its substantial and compelling supporting evidence. One of the most fascinating pieces of evidence is the cosmic microwave background radiation. This faint glow permeating every corner of the universe is essentially the afterimage of that fiery beginning. It represents the residual heat from the initial expansion, the ancient light that was released about 300,000 years after the Big Bang, when the universe had cooled enough for atoms to form and for photons, particles of light, to travel freely through space. This radiation acts like a cosmic fingerprint, a whisper of the universe's infancy preserved across billions of years. Further proof of the Big Bang's validity comes from the observation that distant galaxies are moving away from us, with the farther ones retreating faster. This discovery was groundbreaking, revealing that the universe continues to expand just as it did in its earliest moments. By examining the light emitted from these galaxies, astronomers notice a phenomenon called redshift, where light stretches to longer, redder wavelengths as objects move away. This redshift provides a powerful measure of the universe's ongoing expansion and echoes the explosive origins encoded in its very fabric. These observations combined create an enthralling and coherent narrative about our universe's beginnings, firmly establishing the Big Bang Theory as the prevailing explanation for the cosmos's origin story. But the journey does not end here. Scientists around the world have embarked on an extraordinary quest to deepen our understanding of the universe's inception and its subsequent expansion. This quest has been propelled by cutting-edge technologies and pioneering observational methods. Central to this exploration is the continued study of cosmic background radiation, the subtle afterglow of the universe's explosive birth. By carefully analyzing this radiation, researchers have been able to glimpse snapshots of the universe when it was only a tiny fraction of a second old, revealing vital clues about its temperature, density, and composition at that formative stage. This data provides a window into conditions that existed long before stars or galaxies had even taken shape. Alongside this, astronomers carefully monitor the movement of galaxies to track how space itself is stretching. They do this by studying how light shifts towards the red end of the spectrum, the redshift, a critical method to measure cosmic expansion rates. These observations led to a startling discovery. Not only is the universe expanding, but the rate of expansion is accelerating. This acceleration is attributed to an enigmatic force called dark energy, a mysterious presence that makes up the majority of the universe's total energy content, but remains poorly understood. Understanding dark energy has become one of the greatest challenges in cosmology, sparking intense research and debate. Observational astronomy has greatly benefited from powerful telescopes, both orbiting in space and stationed on Earth. Instruments like the Hubble Space Telescope have transformed our view of the cosmos by capturing breathtaking images of distant galaxies and nebulae. These telescopes also enable scientists to measure distances across the vast expanse of space with unprecedented precision. The development of even more advanced telescopes, capable of detecting light from galaxies formed just a few billion years after the Big Bang, has opened new windows into cosmic evolution, allowing us to trace the universe's growth from its infancy to the present day. Through the synergy of theoretical models, detailed observations, and rapid technological advancement, researchers continue to piece together the complex puzzle of our universe's birth and ongoing expansion. Each new discovery peels back another layer of cosmic history, enriching our understanding and sparking ever deeper curiosity. The pursuit of this knowledge not only illuminates the nature of the cosmos, but also inspires profound reflections on our place within it. Cosmic microwave background radiation remains a cornerstone of this exploration. Often described as the faint glow permeating the entire universe, it serves as a vital clue to the universe's explosive beginning. Imagine this radiation as a remnant echo from that first monumental event, traveling across billions of years and cosmic distances to reach us. Roughly 300,000 years after the Big Bang, the universe had cooled sufficiently for atoms to form and for light to travel unhindered for the very first time. This moment signified the birth of the universe as we perceive it today, a vast, expanding cosmic ocean filled with stars, galaxies, and endless mysteries waiting to be uncovered. As the universe gradually expanded across billions of years, the initial radiant energy it emitted underwent a remarkable transformation. What began as intense light evolved into microwave radiation, a form of energy far too faint for the human eye to perceive directly, yet present everywhere throughout the vast stretches of space. This microwave radiation, known as the cosmic microwave background, or CMB, pervades the cosmos uniformly, almost like the faint hum of a distant radio playing at the lowest volume. Because this radiation maintains an almost perfect temperature balance across the sky, scientists are able to study its subtle variations to unlock secrets about the universe's earliest moments. When astronomers and physicists measure this cosmic microwave background, they detect minute temperature differences, tiny irregularities that carry profound significance. These slight fluctuations represent density variations in the primordial universe, the very early cosmic seeds from which galaxies, clusters, and superclusters eventually grew. These disparities form a kind of cosmic blueprint, showing the initial unevenness in matter distribution that guided the large-scale structure of the universe as it matured over billions of years. This relic radiation serves as a snapshot of the universe in its infancy, capturing a time mere hundreds of thousands of years after the Big Bang, when the cosmos was still an extremely hot, dense plasma gradually cooling down. The presence of the cosmic microwave background radiation stands as one of the strongest pillars supporting the Big Bang theory. It is a tangible remnant of that explosive origin, a detectable afterglow that allows scientists to peer back into the past and understand the universe's evolution. By analyzing this radiation, researchers gain crucial insights into how the universe expanded, cooled, and developed into the complex and vast cosmic landscape we observe today. It not only confirms the idea of a hot, dense beginning, but also provides a detailed map of the early universe's conditions, helping to clarify the timeline and processes that led to star and galaxy formation. Astronomers use multiple approaches to estimate the age of the universe, combining observations of distant celestial objects with theoretical models of cosmic expansion. One fundamental method involves studying the light emitted by faraway galaxies, which carries the imprint of the universe's expansion. The cosmic microwave background radiation itself acts as a cosmic timestamp, an afterglow imprinted with information from the universe's earliest phase. By measuring how fast the universe is expanding, a rate known as the Hubble constant, scientists can work backward in time to determine when the universe began its expansion from a much hotter and denser state. The analogy often used to describe this cosmic expansion is that of a balloon inflating. As the balloon grows, points on its surface move farther apart. Similarly, as the universe expands, galaxies drift away from each other. Knowing the current rate of this expansion allows scientists to estimate how long this stretching has been occurring. This effectively sets a clock on the universe's age, indicating it began roughly 13.8 billion years ago. In addition to observing light and cosmic background radiation, astronomers examine ancient stars and star clusters to refine their understanding of the universe's timeline. Globular clusters, dense collections of some of the oldest stars, have remained relatively unchanged since the universe's youth. These stellar relics act as cosmic chronometers, helping scientists gauge the timing of star formation and evolutionary processes that unfolded in the universe's early epochs. By combining these observational techniques with mathematical models and physical theories, astronomers arrive at a comprehensive estimate for the universe's age and its dynamic history. Understanding the origin and evolution of the universe carries immense importance in modern science. It addresses fundamental questions about existence, creation, and the laws governing the cosmos. Exploring the universe's beginning is not just a scientific endeavor, but a profound inquiry into the nature of reality itself. The Big Bang Theory remains central to this quest, positing that the universe originated from an extraordinarily hot, dense state and has been expanding ever since. Investigating this monumental event helps reveal not only how galaxies, stars, and planets formed, but also how the chemical elements essential for life came into existence. The earliest moments after the Big Bang set the cosmic stage for all subsequent developments. The distribution of matter and energy at that time influenced the formation of the large-scale structures observed today. Furthermore, studying this primordial period challenges and refines our understanding of fundamental physical laws such as gravity and electromagnetism. The extreme conditions present during the universe's birth push the boundaries of current physics, hinting at phenomena or forces yet to be discovered. Dark matter and dark energy, two mysterious components that make up most of the universe's mass and energy, remain enigmatic. Their origins and influence may be better understood by delving deeper into the universe's beginnings. These hidden aspects of the cosmos drive much of its expansion and structure formation, yet their true nature is one of the greatest puzzles in astrophysics. On a philosophical level, contemplating the universe's inception brings up existential questions about our place within the vast cosmos. It invites reflection on the nature of time, space, and causality, as well as the processes that led to a complex, interconnected universe capable of supporting life. Exploring the origin of the universe enriches not only our scientific knowledge, but also our understanding of the fundamental principles that govern reality. The question of what came before the Big Bang remains one of the most profound mysteries in cosmology. This frontier pushes scientists into realms where traditional concepts of time and space may lose meaning. One leading theory is cosmic inflation, which proposes that before the Big Bang, the universe underwent an incredibly rapid expansion. This inflation stretched a tiny, almost infinitesimal region into a vast, smooth cosmos, setting the stage for the Big Bang itself. During this phase, usual notions of time might not apply, making it difficult to define what before truly means. Another intriguing idea is the multiverse hypothesis. This theory suggests that our universe is just one of countless others, each governed by its own physical laws and constants. Our universe could have emerged from interactions or collisions between these alternate realities in a kind of cosmic fertilization process. This opens the door to a much broader understanding of existence, where multiple universes coexist, possibly with vastly different properties. There is also the concept of a cyclical universe, where the cosmos undergoes infinite cycles of expansion and contraction. In this model, what we perceive as the Big Bang is simply the start of a new cycle, born from the collapse of a previous universe. This continual rebirth implies a timeless, ongoing process that transcends the singular event we typically associate with the universe's birth. Some speculate that the fabric of space-time itself might be eternal, with the Big Bang representing just one significant transition within a much larger cosmic continuum. In this view, the Big Bang is not the absolute beginning, but rather a pivotal moment in an ongoing cosmic story that extends infinitely beyond our current understanding. While these theories offer captivating possibilities, they remain largely speculative because empirical evidence predating the Big Bang is extremely difficult to obtain. Each concept challenges our deepest assumptions about reality and invites further inquiry into the profound mysteries that lie beyond our present observational reach. The notion of a singularity is deeply connected to our understanding of the universe's origins, especially within the Big Bang framework. A singularity represents a point where the known laws of physics break down, where density and temperature become infinite and space and time themselves collapse into a single point. This moment, thought to mark the beginning of the Big Bang, is when all matter, energy, space, and time were compressed into an unimaginably small and dense state. When imagining the Big Bang, it is often described as the expansion of this singularity, a sudden and rapid unfolding from a point of infinite density into the vast and complex universe we observe today. This concept, though difficult to fully grasp, forms the cornerstone of modern cosmological thought and continues to drive research into the very fabric of the cosmos, probing the boundary where physics, philosophy, and the mysteries of existence intersect. This immense expansion marked not only the beginning of everything we know, but also the very birth of space and time themselves. Just before this critical moment, our understanding of the universe becomes hazy and uncertain. The scientific laws that normally govern how matter and energy behave suddenly lose their familiar structure and no longer function in the ways we expect. The conditions that prevailed at this point are so extreme and different from anything we experience that they challenge the foundations of physics itself. From this chaotic and dense starting point, the universe began a dramatic phase of rapid inflation, expanding at an unimaginable speed in a fraction of a second. As this rapid growth slowed, the universe cooled down enough to allow particles, such as quarks, electrons, and photons, to form and interact. This set the stage for the gradual assembly of more complex structures, the first atoms, clouds of gas, stars, galaxies, and eventually planets. Everything we see around us, from the vast clusters of galaxies in the depths of space to the tiny grains of dust on Earth, traces its origin back to this incredible birth event. While the singularity acts as the conceptual starting point for the universe, it also raises profound philosophical and scientific questions about the very nature of time and existence. If the universe emerged from such an extraordinary and unique event, what does that say about what came before it, if anything? Was there a before it all, or does time itself only begin at this singularity? What conditions or processes could have existed that led to this violent birth? These questions push us to the limits of scientific inquiry and imagination. Singularities are more than just abstract ideas or mathematical curiosities. They represent the boundary of human understanding, places where our current laws of physics, such as Einstein's theory of general relativity, break down and fail to provide meaningful answers. In exploring these extremes, scientists are forced to look deeper, searching for new theories that can reconcile the nature of gravity with quantum mechanics and provide insights into the origins of the cosmos. One fascinating approach to understanding the universe's life cycle is the cyclic model. This theory proposes that the universe does not have a singular beginning and end, but instead undergoes an infinite series of expansions and contractions. Imagine a balloon. When you inflate it, the balloon expands, representing the universe growing larger over time. When you release the air, the balloon shrinks back down, symbolizing the universe contracting. This cycle of inflating and deflating embodies the essence of the cyclic universe model. According to this concept, after the universe reaches a certain maximum size and cannot sustain its growth any longer, gravity, the force that pulls everything together, begins to dominate. This gravitational pull causes the universe to contract, drawing matter and energy back into an extremely dense and hot state, possibly leading to what is called the Big Crunch. This crushing phase could then set the conditions for another explosive expansion, a new Big Bang, and the cycle begins anew. This cyclical process leads to deep and intriguing questions about the nature of time and existence itself. Each cycle might create a universe similar in some ways to our own, but different enough to follow a unique path of evolution. The cyclic model suggests that traces or imprints of previous universes might linger in subtle ways, potentially detectable as patterns in cosmic radiation or other remnants embedded in the structure of our universe. Despite its appeal and the philosophical elegance of a universe without a definitive beginning or end, the cyclic model faces significant scientific challenges. Our current understanding of cosmic inflation, a period of rapid and smooth expansion following the Big Bang, complicates the idea of a smooth and repetitive transition between cycles. Scientists are still actively investigating how the universe could transition from one phase of expansion to contraction and back again without contradictions or inconsistencies. Studying what happened before the Big Bang presents an even greater challenge. The very fabric of time and space appears to have begun with the Big Bang singularity. Before this, conventional physics no longer applies, making it almost impossible to formulate reliable theories or gather evidence. It is like trying to read a book when the first page is missing. We have no frame of reference or context for what came before. Our understanding of the universe heavily depends on observable evidence, primarily gathered from the cosmic microwave background radiation. This radiation is the faint afterglow of the Big Bang, still detectable billions of years later, and serving as a critical tool for studying the early universe. However, anything that might have existed before the Big Bang remains inaccessible to observation. All information, including light or other signals, would have been compressed or altered beyond recognition, hidden behind the veil of the singularity. Many theoretical models, especially those linking quantum mechanics and gravity, suggest that time itself might not have existed before the Big Bang. Without time, there is no meaningful before or after, no sequence of events to analyze, which challenges our basic understanding of causality. Causality is the principle that every effect has a cause and is a cornerstone of scientific inquiry. In attempts to grapple with these mysteries, scientists explore a range of theories beyond the classical Big Bang model. Cosmic inflation theory tries to explain the early rapid expansion, while multiverse hypotheses suggest that our universe might be one of many, each with different properties and origins. These ideas remain speculative but represent bold efforts to understand the universe's deepest questions. In the end, the birth of the universe is not only a story about the physical world, but also a profound journey into the unknown. It challenges us to rethink time, existence, and reality itself, and invites us to keep searching for answers in the vast cosmic landscape. However, these ideas remain deeply speculative, lacking the firm grounding of empirical evidence. Even as scientists persistently push the boundaries of human understanding through relentless research and groundbreaking technological advancements, the study of what came before the Big Bang remains enveloped in profound mystery. This frontier of cosmology is tethered tightly to the limits of our current scientific frameworks and the very fabric of time itself. Quantum mechanics, a realm that explores the counterintuitive nature of reality at the smallest scales, offers tantalizing clues about the nature of existence, especially when probing moments that might have preceded the Big Bang. Traditionally, the Big Bang has been understood as the absolute beginning of space and time, the origin point from which everything emerged. Yet quantum theories suggest that this narrative may be far more intricate and layered. Imagine the universe not as a simple, unbroken line stretching from a singular origin forward, but as a vast, intricate tapestry woven from countless threads. Each thread represents a potential outcome or a probability, existing in a fluid state of uncertainty before eventually solidifying into the concrete reality that we experience. At the core of this intricate framework lies the concept of quantum fluctuations, random, spontaneous changes in energy occurring even in what appears to be an empty vacuum. Though a vacuum might seem completely empty, quantum mechanics tells us it is anything but. Particles and their antiparticles can spontaneously appear and vanish in the blink of an eye. This suggests that even before the Big Bang, there could have existed a chaotic sea of energy and matter, constantly fluctuating without fixed form or structure. These quantum fluctuations may have sown the seeds for the universe's eventual expansion, creating conditions ripe for the Big Bang to unfold. Another captivating concept that emerges from quantum theory is the multiverse, the idea that instead of a singular universe born from one moment of creation, there may exist an enormous ensemble of universes, each with its own unique laws of physics. Our universe might be merely one bubble floating within a vast, frothy sea of countless other realities. These parallel universes could be expanding alongside ours, operating under physical laws that differ radically from what we observe, or possibly lacking any resemblance to our own existence at all. This radical shift in perspective challenges the long-held notion of a single beginning, instead proposing that the Big Bang could be just one event within an eternal cycle of creation and destruction occurring across multiple realms. Quantum mechanics invites us to rethink the linear narrative of time and causality. Within the quantum domain, time may behave in ways that are profoundly different from our everyday experience. The past and future might be entwined in intricate ways that we are only beginning to comprehend, opening profound questions about the origins of our universe and provoking deep curiosity about what, if anything, existed before the Big Bang. In the fleeting moments following the Big Bang, the universe was an almost unimaginably hot and dense place, a dramatic scene of energy and matter entwined in chaotic turmoil. During this early phase, fundamental forces began to crystallize from the chaos as the universe expanded and cooled. This cooling process set the stage for the formation of the universe's building blocks. Energy started to condense into the fundamental particles that make up everything we recognize today. Quarks and leptons emerged from this primordial soup, a process that can be likened to steam cooling and condensing back into liquid water. Quarks are the fundamental constituents of protons and neutrons, which form the nuclei of atoms. Leptons, a different family of particles, appeared alongside quarks. The most familiar lepton is the electron, an essential part of the atom's structure. As the energy continued to dissipate, quarks began to group into threes, forming protons and neutrons. This process marked the genesis of matter that would eventually assemble into stars, planets, and galaxies. The early universe was not a quiet place, but rather a dynamic environment where these particles interacted intensely through fundamental forces. Imagine a cosmic dance where particles collided, transformed, and influenced each other constantly. This relentless turmoil gave rise to a variety of particles and antiparticles, creating a rich diversity of matter. As our exploration of this era deepens, it becomes clear that the particles formed in this chaotic yet elegant manner laid the essential groundwork for everything that exists today. The interactions and relationships forged during this brief moment shaped the cosmic architecture, leading to the complex and intricate universe we inhabit now. High-energy collisions play a crucial role in the creation of elementary particles. These collisions act as the fuel that transforms energy into matter. Picture two particles hurtling towards each other at unimaginable speeds. When they collide, their kinetic energy, the energy of motion, can become so immense that it converts into new particles. This idea springs from the famous insight that energy and mass are interchangeable, encapsulated by Einstein's equation. During such high-energy collisions, the impact creates an unstable, highly concentrated energy state. This concentrated energy can then condense into various particles according to the principles of quantum mechanics. These newly created particles might include quarks, electrons, or heavier particles like muons, depending on the specific conditions of the collision. Many of these particles are incredibly short-lived, existing only for fractions of a second before decaying back into energy or transforming into more stable forms. This phenomenon is not just a curiosity, but a fundamental process that allows scientists to better understand the building blocks of matter and the forces governing the universe. By observing and analyzing collisions within particle accelerators, machines designed to replicate conditions similar to those just after the Big Bang, researchers peel back layers of the universe's origins, unraveling the profound mysteries embedded in the cosmos. The formation of the first atomic nuclei occurred shortly after the Big Bang, during a phase known as Big Bang Nucleosynthesis. In these earliest moments, the universe was an incredibly hot and dense mixture, dominated by protons, neutrons, and electrons. As the universe expanded and cooled, conditions became favorable for these particles to interact and form simple atomic nuclei. At the very start, when temperatures were extraordinarily high, individual protons and neutrons were unable to settle into stable configurations. The intense heat and energy prevented these particles from binding together, maintaining a chaotic state. However, as the universe continued to expand and the temperature dropped, protons and neutrons began to combine, forging the first atomic nuclei, such as hydrogen and helium. This phase was crucial because it set the stage for all subsequent matter formation. Without these first nuclei, atoms as we know them could never form, and the complex chemistry that underpins stars, planets, and life itself would have been impossible. The conditions and processes during this early nucleosynthesis shaped the elemental makeup of the universe, influencing everything from the stars that light our night sky to the very matter that composes our bodies. Each step in this cosmic evolution, from the flickering quantum fluctuations preceding the Big Bang to the cooling universe giving birth to the first atoms, represents a chapter in the unfolding story of everything we see around us. As we delve deeper into these mysteries, driven by curiosity and the pursuit of knowledge, we come closer to understanding the profound question of our own origins, tracing the lineage of the universe back through time to the very moment when all things began. However, as the universe gradually cooled from its initial fiery state, a remarkable transformation began to take place deep within the fabric of space and time. Protons, tiny particles carrying a positive electrical charge, started to encounter neutrons, which themselves bear no electrical charge, neutral and calm amidst the cosmic turmoil. These encounters were not mere chance collisions, but the very beginnings of a profound process that would forever shape the cosmos. When protons and neutrons fused together, they gave birth to the first atomic nuclei, including helium, along with smaller quantities of other elements like deuterium, a heavier isotope of hydrogen, and lithium. This transformative phase, known as nucleosynthesis, depended heavily on the universe's rapidly changing conditions of temperature and density. There existed only a brief window, lasting mere minutes after the Big Bang, in which the universe's seething energy and matter were precisely balanced to allow these nuclear reactions to take place. During this short cosmic infancy, the elemental makeup of the universe began to solidify. Roughly 3/4 of the mass of the universe became hydrogen nuclei, the simplest and most abundant building block of matter, while helium nuclei formed a smaller yet significant fraction. Traces of deuterium and lithium also emerged, setting the stage for all the chemistry and complexity that would follow. As the universe continued to expand and cool, the energy became insufficient to sustain free-floating charged particles. This cooling allowed electrons, tiny negatively charged particles, to combine with these positively charged nuclei, forming neutral atoms for the first time. This monumental event, called recombination, marked the universe's transition from a hot plasma to a transparent cosmos where light could travel freely. The creation of neutral atoms was crucial because it set the stage for the formation of the first stars, galaxies, and eventually the intricate cosmic web we observe today. From what began as a chaotic, energetic soup of elementary particles emerged the very foundation of all matter. Nuclear synthesis, the process by which elements are formed through nuclear reactions, played a central role in this unfolding cosmic drama. To fully grasp its importance, one must travel back to those earliest moments after the Big Bang, when the universe was unimaginably hot and dense, filled primarily with subatomic particles such as protons, neutrons, electrons, and photons. As expansion proceeded, the universe's temperature dropped, and conditions gradually became suitable for particles to combine and form the simplest elements, mainly hydrogen and helium. This phase, referred to as Big Bang nucleosynthesis, lasted only a few minutes but was extraordinarily consequential. The universe at that time was a cosmic furnace, where the fusion of protons into helium and traces of lithium occurred, effectively laying the chemical groundwork for everything that would come later. With time moving forward and the universe's expansion persisting, vast clouds of gas began to collapse under the pull of gravity, giving rise to the very first stars. These early stars ignited nuclear fusion deep within their cores, producing the extreme heat and pressure necessary to forge heavier elements beyond hydrogen and helium. Through a process known as stellar nucleosynthesis, elements like carbon, oxygen, and iron were synthesized in the stellar furnaces. This generation of stars became the cosmic alchemists, transforming the primordial hydrogen and helium into a richer elemental variety. The life cycle of stars often culminated in spectacular explosions called supernovae, events so powerful that they scattered the newly formed elements far and wide across the universe. These explosive deaths enriched the interstellar medium, the vast expanses of gas and dust between stars, with a complex mixture of elements seeding the material that would later form new stars, planets, and eventually life itself. Without this cosmic recycling, the elemental diversity necessary for planets and living organisms would not exist. Today, the very atoms that make up our bodies, carbon, nitrogen, phosphorus, and many others, trace their origins to these ancient processes of nucleosynthesis, occurring both in the moments after the Big Bang and within the fiery hearts of stars. This chain of cosmic events not only shaped the chemical complexity of the universe, but also fundamentally influenced the formation of galaxies, stars, planets, and the emergence of life. In modern times, scientists have developed powerful instruments known as particle accelerators, which function as miniaturized laboratories to recreate conditions similar to those of the early universe. These machines act as cosmic colliders, accelerating tiny particles such as protons to incredible speeds approaching that of light itself. When these particles collide, they unleash enormous bursts of energy, sometimes converting that energy into new particles, mirroring the process by which energy transformed into matter in the universe's infancy. The significance of these collisions lies in their ability to produce conditions so extreme that new, often rare particles can emerge, allowing researchers to probe the fundamental forces and interactions governing the cosmos. By carefully analyzing the particles created in these high-energy collisions, scientists can glean insights into the nature of the matter that once filled the early universe, helping to unlock mysteries about its composition and evolution. One focus of this research is the study of fundamental constituents like quarks and gluons, the tiniest building blocks of protons and neutrons, which are believed to have existed freely in a hot, dense state before cooling and condensing into the particles we observe today. These elementary particles were the primordial soup from which all known matter eventually emerged, offering a glimpse into the universe's earliest moments and the processes that shaped everything we see around us. Thus, the story of nucleosynthesis, from the fusion of protons and neutrons mere minutes after the Big Bang to the fiery cores of stars and the cataclysmic explosions of supernovae, weaves a rich narrative. It is a narrative of transformation and creation, linking the tiniest particles to the vast galaxies, the stars, and ultimately the life that ponders its own cosmic origins. Additionally, particle accelerators serve as powerful tools that allow scientists to probe the fundamental fabric of the cosmos, reaching back to the earliest moments of the universe's existence. These colossal machines, through the collisions they produce at incredibly high energies, test the very theories that describe how the universe began and evolved. By smashing particles together at speeds approaching the speed of light, particle accelerators recreate conditions similar to those just after the Big Bang. Within these violent, energetic collisions, physicists search for elusive entities such as various types of Higgs bosons and exotic mesons, particles that may shed light on the deepest layers of physical reality. Moreover, these experiments offer tantalizing hints about the mysterious nature of dark matter, an invisible substance that is thought to make up a large portion of the universe's mass, but remains undetected by conventional means. The process involves comparing experimental results obtained from these collisions with predictions made by sophisticated theoretical models, enabling physicists to either confirm or challenge our current understanding of the universe's formation and the fundamental laws governing it. In this way, particle accelerators act as scientific time machines, granting humanity a rare glimpse into the primal conditions that shape the cosmos. Each experiment peels back another layer of the universe's complex story, revealing how particles first formed and interacted in the cosmic dawn. This ongoing research enriches the narrative of the origins of everything we observe today. Rewind to the very beginning, shortly after the Big Bang, when the universe was unimaginably hot and dense. Picture a vast, turbulent sea of energy and fundamental particles, all moving at extraordinary speeds within an expanding space. As the universe expanded, it began to cool, allowing particles to coalesce in a process known as nucleosynthesis. This process marked the assembly of the universe's earliest building blocks, primarily protons and neutrons, which later combined to form the nuclei of simple atoms. Just a few minutes after the Big Bang, as temperatures dropped sufficiently, protons, the positively charged components of atomic nuclei and the essential building blocks of hydrogen, began to join with neutrons, forming the nuclei of helium atoms. Almost simultaneously, the remaining free protons combined with electrons, creating the first hydrogen atoms. This primordial synthesis resulted in a universe composed mostly of hydrogen and helium, with roughly 1 helium atom for every 3 hydrogen atoms. This elemental mixture became the foundation for the entire cosmic structure that followed. Over billions of years, under the influence of gravity, these hydrogen and helium atoms gathered to form the first stars and galaxies, crafting the rich cosmic tapestry we witness today. The formation of these two elements did more than just mark the birth of matter. It set the stage for all subsequent cosmic complexity. In those earliest moments, the universe was a hot, dense expanse dominated by hydrogen and helium. As it expanded and cooled, these simple elements provided the essential scaffolding for the emergence of stars and galaxies. Yet the universe was initially devoid of heavier elements that are critical for the diversity and complexity of matter we encounter now. The creation of these heavier elements began later, deep within the fiery hearts of stars, through a remarkable process called nuclear fusion. Within stars, intense gravitational forces compress the stellar core to incredibly high densities and temperatures. This environment allows hydrogen atoms to collide and fuse, forming helium in a chain of reactions that release prodigious amounts of energy. This energy sustains the light and heat emitted by stars. As stars age and exhaust their hydrogen fuel, their cores contract further and temperatures rise, enabling the fusion of helium into progressively heavier elements such as carbon and oxygen. This cycle of fusion continues, enabling stars to synthesize heavier and heavier elements, culminating at iron. Iron represents a critical threshold in stellar nucleosynthesis because fusing iron nuclei requires energy input rather than releasing energy. Thus, iron fusion is energetically unfavorable, marking the endpoint for energy-generating nuclear fusion within stars. When massive stars exhaust their fuel, they undergo dramatic transformations, often culminating in catastrophic explosions called supernovae. These supernovae are among the most energetic events in the universe, scattering the heavy elements forged inside the stars across the cosmos. The explosion creates extreme conditions that facilitate the rapid capture of neutrons by atomic nuclei, known as the Rapid Neutron Capture Process, or R process. This mechanism allows the formation of some of the heaviest elements in the universe, including gold, uranium, and other precious metals. The aftermath of these cosmic detonations enriches the interstellar medium, the vast space between stars, with these heavy elements. Over time, this enriched material becomes incorporated into new generations of stars, planets, and eventually living organisms. In this way, the cycle of stellar evolution and cosmic cataclysms is responsible for the very building blocks that constitute planets, life, and everything in between. Stellar nucleosynthesis is an extraordinary process unfolding within stars that act as cosmic furnaces where lighter elements are fused into heavier ones. Imagine a star beginning its life as a massive cloud of hydrogen gas. Within its core, under intense heat and pressure, hydrogen nuclei collide and fuse to form helium, releasing vast amounts of energy. This energy manifests as the radiant light and warmth we associate with stars. As stars mature, their internal processes evolve. When hydrogen is depleted, the star's core begins to fuse helium, creating elements like carbon and oxygen, essential for the chemistry of life and planetary formation. This transformation is critical because it not only produces new elements, but also paves the way for the synthesis of even heavier atoms as the star progresses through its life stages. When a star reaches the end of its life, especially during a supernova explosion, it releases into space the elements formed within its core. The extreme conditions of the explosion allow the creation of elements heavier than iron through rapid neutron capture. Thus, each generation of stars contributes to the cosmic diversity of elements distributed across the universe. The remnants of stellar nucleosynthesis enrich the interstellar medium, providing the raw materials for new stars, planets, and ultimately the emergence of life. Every atom in our bodies that is heavier than hydrogen was once forged in the heart of a star, linking us intimately to the life cycles of these distant celestial furnaces. Understanding stellar nucleosynthesis offers profound insight into how the universe evolves and how the variety of elements found throughout the cosmos forms the foundation for the rich complexity of matter that surrounds us today. The story of element creation is a tale written in the stars, illuminating our place within the vast universe and connecting the smallest particles to the grandest cosmic structures. Supernovae play an indispensable role in the grand tapestry of the cosmos, functioning as immense stellar foundries, where elements are both forged and dispersed across the vast expanse of the universe. When a massive star approaches the twilight of its existence, it can erupt in a cataclysmic explosion known as a supernova. This event is not merely a dazzling celestial display, but a critical juncture in the life cycle of matter itself, marking the transformative passage from simple stellar ingredients to the complex assortment of elements that form planets, life, and the very fabric of reality. Throughout a star's long and dynamic life, nuclear fusion within its core acts as an engine of creation, melding lighter atoms into heavier counterparts. Hydrogen atoms collide and combine to form helium in a relentless process fueled by the immense gravitational pressure and heat at the star's center. As the star matures, the fusion process progresses to heavier elements. Helium atoms fuse to create carbon, carbon can fuse into oxygen, and so on, producing an array of elements up to iron. This progressive synthesis unfolds over millions to billions of years, painting a portrait of stellar alchemy in action. However, the true marvel of elemental creation occurs at the supernova's explosive finale. In the final throes of the star's demise, the core collapses under its own gravity, triggering temperatures and pressures so extreme that elements heavier than iron begin to form in rapid succession. This intense environment enables the fusion of nuclei into precious metals like gold and silver, as well as radioactive elements such as uranium. These elements are born in moments of extraordinary energy release, born in the furnace of a star's violent death throes. Once the supernova explodes, it ejects this cosmic bounty outward, scattering a rich mixture of newly minted elements into the interstellar medium. This dispersed material becomes the essential seedbed for future generations of stars, planets, and potentially habitable environments. It is akin to a cosmic chef scattering essential ingredients across a vast kitchen, ensuring that the recipe of the universe continues to evolve. The remnants of supernova explosions also contribute to the cosmic dust and gas clouds, which themselves serve as the raw building blocks from which new celestial bodies arise. The cycle of stellar birth, death, and rebirth driven by supernovae exemplifies the ongoing evolution of the universe. These explosive events are not merely the spectacular conclusions to a star's life. They are fundamental processes that enrich the cosmos with the very elements necessary for the formation of planets, the emergence of life, and ultimately our own existence. The complex web of chemical reactions and physical forces that govern these processes have shaped the universe from its earliest moments. In the primordial aftermath of the Big Bang, the universe was an extreme environment dominated primarily by hydrogen and helium, the lightest and simplest elements. Through gravitational forces, clouds of these gases began to collapse, their increasing density igniting the first nuclear furnaces, stars. Within these incandescent spheres, fusion converted hydrogen into helium, and as the stars aged, they generated progressively heavier elements such as carbon and oxygen. When the most massive of these stars ended their lives in spectacular supernova explosions, they released their elemental treasures, spreading the raw materials for future chemical interactions. This dispersal of elements across the cosmos created fertile environments for complex chemical reactions, leading to the formation of gas and dust clouds that eventually coalesced into new stars and planetary systems. On our own planet Earth, as conditions stabilized billions of years later, the elements combined in increasingly intricate ways. Simple molecules formed and gave rise to organic compounds essential for life. These molecules laid the foundation for the emergence of self-replicating structures, the forerunners of living organisms. From the primordial soup rich in organic chemicals, the intricate dance of chemistry led to the creation of DNA, proteins, and cellular systems that constitute the biological complexity we witness today. The continual cycles of chemical transformation within Earth's atmosphere, oceans, and living beings illustrate the fundamental role that reactions play not only in biology, but across geological and astronomical realms. The universe itself can be viewed as a vast and dynamic symphony of chemical interactions, where every reaction, no matter how minute, contributes to the ongoing narrative of existence. This grand interplay bridges the gulf between the simplest atomic elements and the intricate life forms that inhabit our world. In contemporary scientific thought, especially in cosmology and physics, the concept of nothing transcends everyday understanding. In common language, nothing often denotes a simple absence, an empty room devoid of people or objects. Yet scientifically, nothing is far more complex. At the quantum level, a perfect vacuum, space free from matter, is not truly empty. Instead, it teems with energy fluctuations where particles briefly emerge and vanish, a phenomenon known as quantum foam. These ephemeral particles and energy fluctuations mean that even the emptiest parts of space are alive with potential and activity. The universe itself is thought to have originated from an incredibly high energy state, challenging our intuitive notions of nothing. Some cosmologists theorize that the universe emerged from a quantum vacuum state, a seething backdrop of energy and potentiality rather than an absolute void. This conception challenges the very idea of a barren void and suggests that what we perceive as nothingness is in fact a vibrant, dynamic field full of possibility. When contemplating the vacuum of space, it may appear at first glance to be a perfect emptiness, a total void lacking any substance. Yet, science reveals that this apparent emptiness conceals a complex realm of invisible processes and energetic fluctuations. These unseen dynamics challenge human intuition and invite profound reflection on the nature of existence itself, like emphasizing that the fabric of reality is far richer and more intricate than it might initially appear. This intricate cosmic narrative, from the fiery deaths of stars to the invisible quantum dance in the vacuum, underscores the continuous transformation and renewal at the heart of the universe. Each element forged in the furnace of a supernova, every chemical reaction in distant clouds of gas, and the very quantum fluctuations within the emptiest space collectively compose of ongoing creation, evolution, and connection that links the smallest particles to the grandest cosmic structures and life itself. However, the concept of vacuum fluctuations introduces a fascinating twist to the traditional understanding of emptiness in the cosmos. According to the principles of quantum physics, what we often perceive as a complete vacuum, a space devoid of matter and energy, is far from empty. Instead, it is a roiling sea of activity at the smallest scales imaginable, where the very fabric of reality is alive with ephemeral particles that emerge and vanish in the blink of an eye. This phenomenon is rooted in the uncertainty principle, a fundamental aspect of quantum mechanics, which dictates that certain pairs of physical properties cannot both be precisely known simultaneously. As a result, energy can briefly fluctuate, allowing particles to pop in and out of existence seemingly from nowhere. This raises profound questions that stretch beyond the limits of current human comprehension. Where did these particles originate? What is the nature of the vacuum itself? And at a grander scale, who or what brought the universe into being? What if everything we observe, the stars twinkling in the night sky, the planets tracing their orbits, the vast galaxies scattered across the cosmos, is merely a faint echo or a subtle whisper of an ancient, unseen past? The universe, teeming with staggering complexities and enigmas, began not from a simple point, but from an event so immense and unimaginable that its reverberations still ripple across space and time today. Are we on the cusp of unraveling the secrets of our cosmic origins? To embark on this journey, we must first confront the grand narrative that frames much of our modern understanding. The Big Bang Theory. This model describes the origin of the universe as a rapid expansion from an extremely hot and dense state, where all matter and energy were compressed into a space smaller than a grain of sand. Approximately 14 billion years ago, this concentrated seed burst forth in a swift expansion, not as a typical explosion centered at a particular spot, but as an expansion of space itself stretching outward in all directions. As the universe expanded, it gradually cooled, allowing subatomic particles to form, including protons, neutrons, and electrons. These primordial particles later combined to create the first simple atoms, predominantly hydrogen and helium, which began to gather into immense clouds. These clouds, driven by the inexorable pull of gravity, collapsed to ignite the first stars and birth galaxies. The Big Bang Theory stands as the most robust explanation for the universe's origin, supported by a wealth of observational evidence. Among the most compelling is the cosmic microwave background radiation, a faint glow permeating the universe that represents the leftover heat from that initial expansion. This radiation acts as a fossil record, an echo of the intense energy state that existed moments after the birth of the cosmos. Further evidence emerges from observations of distant galaxies moving away from us, their light stretched toward the red end of the spectrum, a phenomenon known as redshift. The farther a galaxy is, the faster it appears to recede, providing a clear indication that the universe is still expanding today, just as it has been since the moment of the Big Bang. This expanding cosmos is not slowing down, it is accelerating, propelled by a mysterious force known as dark energy, whose true nature remains one of the greatest puzzles in contemporary physics. To explore these mysteries, scientists have embarked on an extraordinary quest, combining cutting-edge technology and ingenious observational methods. Telescopes like the Hubble Space Telescope have revolutionized our view of the universe, capturing breathtaking images of distant galaxies and nebula, while measuring vast cosmic distances with unprecedented precision. Recent advancements have pushed the boundaries even further, enabling astronomers to glimpse galaxies formed just a few billion years after the Big Bang, providing invaluable insights into the universe's early evolution. Central to this exploration is the study of cosmic microwave background radiation, the afterglow of the Big Bang itself. By meticulously analyzing this faint, uniform radiation, researchers have been able to construct detailed snapshots of the infant universe, mere fractions of a second after its inception. These observations reveal vital clues about the temperature, composition, and large-scale structure of the cosmos at its earliest stages, painting a picture of a universe evolving from a hot, dense state toward the complex, structured expanse we inhabit today. Additionally, by studying the redshift of galaxies, scientists measure the rate of cosmic expansion, uncovering the accelerating pace driven by dark energy. This remarkable discovery challenges existing theories and propels new avenues of research into the fundamental forces shaping our universe. The synergy between theoretical models, astronomical observations, and technological innovation continues to deepen our understanding of the universe's birth and its ongoing transformation. Cosmic microwave background radiation, often described as the faint glow of the universe itself, serves as a crucial pillar supporting the Big Bang Theory. Imagine this radiation as a relic, a whisper from a time roughly 300,000 years after the Big Bang, when the universe had cooled sufficiently to allow atoms to form and photons, the particles of light, to travel freely for the first time. This moment, known as the era of recombination, marks the dawn of the universe as we perceive it today, the moment when the cosmos transitioned from an opaque, fiery plasma to a transparent expanse filled with light. In this unfolding cosmic story, every discovery enriches our knowledge and fuels our curiosity, inviting us to ponder not only where we come from, but what mysteries the universe still holds. As humanity peers ever deeper into the cosmos, the quest to understand our origins becomes an epic saga blending the smallest quantum fluctuations with the grandest cosmic scales, revealing a universe that is at once astonishingly vast and profoundly intimate. As the universe unfolded over the course of billions of years, an extraordinary transformation took place. The initial burst of light, born in the earliest moments of existence, gradually shifted into a form far beyond the grasp of our human eyes: microwave radiation. This cosmic afterglow, known as the cosmic microwave background radiation, pervades every corner of space, saturating the vast expanse of the cosmos with a faint hum that resembles the distant static of a radio tuned to a low volume. Despite its subtlety, this radiation is uniform in its spread, a ghostly, persistent presence that whispers the story of our universe's earliest chapters. The temperature of this radiation is nearly perfect in its steadiness, a fact that allows scientists to peer back into the primordial universe with incredible precision. By meticulously analyzing its uniformity, researchers unlock secrets about the conditions that existed mere moments after the universe's birth. However, what truly captivates astronomers and cosmologists alike are the minute variations in this radiation's temperature, tiny fluctuations that act as cosmic fingerprints, pointing to the universe's infancy when matter was not yet evenly spread out. These subtle irregularities hint at the primordial density fluctuations from which galaxies, stars, and immense cosmic structures would eventually emerge, shaping the architecture of everything we see today. The cosmic microwave background radiation serves as a snapshot of the universe's infancy. It is the oldest light that still lingers, a remnant from the time when the cosmos was a newborn, hot and dense. Its existence not only lends powerful support to the Big Bang theory, the leading explanation for the universe's origin, but it also provides a portal into understanding the universe's evolution over eons. By studying this radiation, scientists refine their grasp of how the universe expanded, cooled, and transformed, laying the foundation for the complex cosmos in which we reside. Astronomers estimate the universe's age by observing distant celestial objects and applying the principles of cosmic expansion. A cornerstone of this effort is the study of light emitted by faraway galaxies, alongside the properties of the cosmic microwave background radiation itself. This afterglow from the Big Bang carries an immense trove of information about the early universe, including patterns and temperature maps that allow for detailed analysis. Central to these calculations is the Hubble constant, a measure of the universe's expansion rate. By understanding how quickly space is stretching, scientists can rewind cosmic time, effectively tracing the timeline back to when the universe was denser and hotter and determining the approximate moment of its origin. To visualize this, imagine a balloon inflating. As the balloon grows, the distance between any 2 points on its surface increases. Similarly, as the universe expands, galaxies drift further apart. Knowing the rate of this expansion enables cosmologists to estimate how long this process has been ongoing. This approach has yielded an age estimate of approximately 13.8 billion years, a testament to the intricate web of evidence woven from observational data, mathematical models, and theoretical frameworks. Complementing these observations, astronomers turn to the oldest stars and star clusters in the universe. In particular, globular clusters, dense groupings of ancient stars, have remained relatively unchanged since the universe's earliest epochs. These stellar relics serve as cosmic clocks, their ages providing crucial clues about the timing of star formation and the universe's developmental stages. By combining data from distant galaxies, microwave background measurements, and stellar chronometers, researchers assemble a comprehensive timeline of cosmic history. Understanding the universe's beginnings holds profound significance in modern science, as it touches upon fundamental questions about existence, creation, and the underlying laws that govern reality. Exploring the origin of the cosmos is a gateway to unraveling mysteries about how everything came to be, from the smallest particles to the vast cosmic web. It offers insight into the fabric of space and time itself, guiding humanity's quest to comprehend the grandest scales of reality. At the heart of this exploration lies the Big Bang theory, which posits that the universe emerged from an unimaginably hot and dense state. Investigating this primordial event sheds light not only on the formation of galaxies, stars, and planets, but also on the creation of the chemical elements essential for life. The earliest moments define the distribution of matter and energy, setting the stage for the large-scale structures we observe today. Delving into the universe's infancy also tests the boundaries of contemporary physics. The extreme conditions present during the Big Bang push our understanding of fundamental forces such as gravity and electromagnetism to their limits. This endeavor may even reveal new physical laws or phenomena beyond current knowledge. Mysteries such as dark matter and dark energy, enigmatic substances making up most of the cosmos, might find their origins illuminated through these investigations. On a philosophical level, the quest to understand the universe's inception prompts reflection on humanity's place within the cosmos. It challenges us to contemplate the nature of time, space, and causality, inspiring questions about how a complex web of interactions, including life itself, emerged from the universe's earliest state. This journey enriches both our scientific understanding and our appreciation for the intricate tapestry of existence. The question of what existed before the Big Bang opens a frontier of theoretical physics, where conventional notions of time and space become uncertain. One leading hypothesis is cosmic inflation, a brief period of exponential expansion that transformed a tiny minuscule region into the vast, homogeneous universe we observe. During this phase, traditional concepts of time might not apply, suggesting a reality where familiar laws of physics give way to something profoundly different. Another fascinating idea is the possibility of a multiverse, where our universe is but one among countless others, each governed by its own physical laws. In such a scenario, the birth of our universe could result from interactions or collisions among these universes, a cosmic fertilization of sorts. This expands the boundaries of what we consider reality, hinting at a grander cosmic landscape. There is also the concept of a cyclical universe, which proposes that the cosmos undergoes endless cycles of expansion and contraction. Here, the Big Bang is not an absolute beginning, but the start of a new cycle following the collapse of a previous universe. Such a model introduces the possibility of a timeless existence beyond the Big Bang, where cosmic history loops endlessly. One more speculative idea considers space-time itself as eternal, with the Big Bang representing merely a transitional phase in a vast continuum of cosmic evolution. From this perspective, the Big Bang is not the birth of everything, but a significant event within a much larger cosmic saga. Despite their intriguing implications, these theories remain speculative due to the difficulty of acquiring empirical evidence about conditions before the Big Bang. Each pushes the limits of our understanding, challenging the very nature of reality and inviting ongoing inquiry into the universe's deepest mysteries. A critical concept entwined with the universe's origin is that of the singularity. This refers to a point in space where known laws of physics collapse, where matter, energy, space, and time compress into an infinitely small point of infinite density and temperature. The Big Bang is often described as the moment this singularity began its expansion, giving rise to the cosmos as we observe it today. This singularity stands as both a profound mystery and a foundation of modern cosmology, representing a threshold where our scientific theories struggle to penetrate. It marks the boundary between the unknown and the known, between the pre-universe and the unfolding reality of space and time. The study of this boundary continues to inspire and challenge physicists, driving the quest to understand not just the universe's beginning, but the fundamental nature of existence itself. This immense expansion marked not just an event, but the very birth of space and time themselves. Before this transformative moment, our understanding of the universe dissolves into uncertainty, as the established laws of physics, the very principles we rely on to explain reality, fail to apply in the way we expect. The universe, emerging from a state so chaotic and dense, entered an extraordinary phase of rapid inflation. This expansion was astonishingly swift, causing space itself to stretch faster than the speed of light, a process that dramatically cooled the universe and allowed particles, the fundamental building blocks of matter, to come into existence. This stage laid the essential groundwork for the formation of everything we observe today: galaxies, stars, planets, and all cosmic structures. At the heart of this story lies the singularity, the enigmatic point that serves as the universe's starting point. However, this singularity is far more than a mere beginning. It is a profound mystery that challenges our deepest concepts of time and existence. If the entirety of our universe sprang from such an extraordinary phenomenon, it forces us to question what, if anything, preceded it. What conditions in the cosmos could have triggered this dramatic birth? Was there some kind of before, or is time itself a construct born at this very instant? The singularity represents the boundary where our current scientific understanding hits a wall, pushing us to explore realms beyond known physics. One captivating framework that offers a different outlook on the universe's origins is the Cyclic model. This perspective imagines the universe not as a one-time event, but as part of an endless series of expansions and contractions. To visualize this, picture a balloon. When you inflate the balloon, it represents the universe growing and expanding. When you release the air, the balloon deflates, shrinking back down. According to the Cyclic model, the universe undergoes similar cycles of inflation and contraction. After expanding for billions of years, gravity, the force that pulls matter back together, eventually halts this growth and triggers a contraction phase. This contraction might culminate in a big crunch, a state where matter and energy collapse into an incredibly dense form, possibly sparking another Big Bang and the beginning of a new cycle. This cyclical dance between expansion and contraction raises profound questions about the very nature of time and existence. Each cycle could theoretically give birth to a universe similar yet different, allowing for distinct evolutionary paths of galaxies, stars, and even life itself. Moreover, this model suggests that traces or patterns from previous cycles could be embedded in our current universe, waiting to be discovered by scientists through subtle imprints in cosmic background radiation or large-scale cosmic structures. Despite the allure of the cyclic model, it faces formidable scientific challenges. The theory of cosmic inflation, describing a rapid and smooth expansion immediately following the Big Bang, complicates the idea of a seamless transition between cycles. The precise mechanisms that would allow the universe to contract and bounce back remain speculative, and current observations sometimes seem at odds with the cyclic scenario. Still, this model propels ongoing scientific exploration, pushing us to probe deeper into the cosmos and rethink the origins and potential destiny of our universe. One of the greatest difficulties in understanding what came before the Big Bang is that time itself appears to begin at the singularity. Before this event, conventional physics breaks down. The familiar fabric of space and time is no longer applicable. Trying to explore this before is like attempting to read a book with its first pages missing. There is no context or framework to comprehend what existed prior. Our current understanding is deeply tied to observable evidence, primarily the cosmic microwave background radiation, the faint afterglow left by the Big Bang. This radiation provides a glimpse into the universe's infancy, but tells us nothing about what, if anything, existed beforehand. The concept of time prior to the Big Bang is especially challenging. Quantum mechanics and theories that attempt to unify it with gravity suggest that time as we know it may not have existed before this primordial event. Without time, the sequence of cause and effect breaks down, making it impossible to meaningfully discuss before. This shatters our intuitive understanding of causality, the very principle science relies upon to explain phenomena. Some theoretical models attempt to bridge this gap. Quantum cosmology, for example, posits that the universe could have emerged from a quantum vacuum, a seething sea of energy where particles and antiparticles spontaneously appear and vanish. This vacuum is far from empty. It is a dynamic field where fluctuations occur constantly. These quantum fluctuations could have acted as seeds for the universe's creation, leading to the conditions necessary for the Big Bang's explosive birth. The notion of a multiverse emerges naturally from quantum theory as well. Instead of a singular beginning, there might be countless universes, each with its own laws of physics, its own timeline, and perhaps its own Big Bang. Our universe could be just one bubble in a vast cosmic foam, expanding alongside myriad others. Some might be vastly different, governed by physics we can scarcely imagine. This concept challenges the idea of a unique beginning, hinting at an eternal, almost infinite landscape of creation and destruction across countless realms. Quantum mechanics invites us to rethink time not as a simple linear flow, but as a complex tapestry where past, present, and future intertwine in strange and subtle ways. In the quantum realm, time may behave very differently, blurring the boundaries between what came before and what comes after. This profound reimagining of time opens new possibilities for understanding our universe's origins and the nature of existence itself. In the moments following the Big Bang, the universe was an unimaginably hot and dense environment. This extreme state was a chaotic soup of energy and matter, where the fundamental forces of nature began to separate and take shape. As the universe expanded and cooled, conditions became suitable for particles to coalesce and form the building blocks of matter: quarks, electrons, and photons. These particles would later combine to create atoms, leading to the formation of stars, galaxies, and everything else we see in the cosmos today. The journey from that primal moment to the vast, structured universe we inhabit is a story of transformation and complexity, driven by fundamental physical laws, yet still containing mysteries that push the boundaries of human understanding. Each discovery in cosmology reveals not only answers, but also new questions, inviting us to continue exploring the infinite enigma that is our universe. Imagine the earliest moments of our universe as a vast, turbulent cosmic cauldron, filled with an unimaginably hot, dense, and energetic primordial soup. In this seething chaos, the very fabric of matter began to take shape, much like steam cooling and condensing back into water droplets in a mist. At the heart of this transformation were the most fundamental building blocks of matter: quarks and leptons. Quarks emerged first, forming the essential foundation of protons and neutrons, the particles that would become the core components of atomic nuclei. These quarks, tiny and elusive, did not exist in isolation for long. Alongside them appeared leptons, a different family of particles with distinct characteristics. Among leptons, the electron stands as the most familiar and vital participant in the architecture of atoms, orbiting the nucleus and enabling the formation of chemical bonds and the vast complexity of matter as we know it. As the cosmic energy levels gradually decreased with the expansion of the universe, quarks began to combine in groups of three, assembling into protons and neutrons. This step marked a critical juncture, the creation of matter capable of building the stars, planets, and galaxies that fill the cosmos. But this was no simple static assembly. Instead, the early universe resembled a grand cosmic dance floor where particles moved, collided, and transformed in a continuous, dynamic interplay governed by the fundamental forces of nature. Each collision and interaction not only produced new particles, but also led to the creation of antiparticles, enriching the diversity of matter and antimatter within this young universe. The interactions between these elementary particles and their antiparticles shaped the cosmic environment in ways that would ripple through time, establishing the foundational structure upon which everything else would be built. The relationships and forces set in motion during this tempestuous era crafted the intricate cosmic architecture we observe today, influencing the formation and evolution of all matter, from the smallest atoms to the largest galactic clusters. Central to this process of creation are high-energy collisions, which serve as the engines driving the transformation of energy into matter. Picture two particles hurtling toward one another at speeds approaching the speed of light. When they collide, the kinetic energy, the energy of motion, becomes so concentrated and intense that it momentarily creates a dense, unstable pocket of energy. Within this fleeting burst of energy, governed by the strange and counterintuitive rules of quantum mechanics, new particles can spontaneously materialize. This phenomenon echoes the profound insight that energy and mass are interchangeable, famously encapsulated by Einstein's equation, E equals mc squared. Depending on the collision's energy and conditions, the newly formed particles can range from familiar entities like quarks and electrons to heavier, less stable particles such as muons. These particles often exist for mere fractions of a second before decaying back into energy or transforming into more stable forms, a transient yet vital process that provides scientists with a window into the fundamental makeup of the universe. By studying these ephemeral creations in particle accelerators, gigantic machines that replicate the conditions just moments after the Big Bang, researchers gain invaluable insight into the forces that govern everything from the tiniest particles to the vast cosmic web. Shortly after the universe's fiery birth, during a phase known as Big Bang nucleosynthesis, the first atomic nuclei began to form. Initially, the universe was a boiling hot mix of protons, neutrons, and electrons swirling in an energetic dance. As the universe expanded and cooled, conditions became just right for these particles to collide and fuse, forming the simplest nuclei. At first, the extreme heat prevented stable combinations. But as temperatures dropped, protons, positively charged particles, began to merge with neutrons, which carry no electric charge. This fusion led to the creation of helium nuclei, alongside smaller amounts of deuterium and lithium. This delicate process unfolded during a narrow window of just a few minutes after the Big Bang. Within this brief cosmic moment, approximately 3/4 of the universe's mass became hydrogen nuclei, the simplest and most abundant element, while helium and other light elements constituted smaller fractions. As cooling progressed, electrons finally combined with these nuclei, neutralizing their charge and giving birth to the first atoms. This milestone set the stage for the universe's further evolution, ultimately enabling the formation of stars, galaxies, and all the complex structures that followed. Nucleosynthesis, the formation of new elements through nuclear reactions, is a cornerstone in understanding the universe's chemical evolution. After the Big Bang forged the primordial light elements, clouds of gas began to collapse under the force of gravity. These collapses birthed the very first stars, stellar furnaces where intense heat and pressure ignited nuclear fusion. Within these stellar cores, hydrogen atoms fused to form heavier elements like carbon, oxygen, and iron through processes collectively known as stellar nucleosynthesis. When stars reach the end of their life cycles, many explode in spectacular supernovae, cataclysmic events that scatter these newly formed heavy elements across the cosmos. This cosmic enrichment transformed the interstellar medium, seeding future generations of stars and planets with the building blocks of complexity. Today, the essential elements for life itself, carbon, nitrogen, phosphorus, and others, owe their existence to these ancient stellar processes. Nucleosynthesis, therefore, is not merely a cosmic curiosity. It is the process that created the elemental diversity, enabling the rise of galaxies, stars, planets, and ultimately life. Particle accelerators serve as our time machines, recreating the extreme conditions of the universe's infancy. These colossal machines propel tiny particles, such as protons, to velocities approaching the speed of light, orchestrating collisions of incredible energy. In these fleeting, powerful encounters, energy transmutes into matter, birthing new particles in ways reminiscent of the primordial transformations that occurred billions of years ago. The significance of these collisions lies in their ability to unveil the hidden forces and interactions shaping the universe's fundamental structure. By analyzing the debris from these collisions, scientists delve deep into the nature of the elementary particles, quarks, leptons, gluons, and the forces binding them together. These insights reveal how matter behaved in the hot, dense state before the universe expanded and cooled, offering glimpses into conditions impossible to replicate anywhere else. The research conducted through particle accelerators continues to push the boundaries of our understanding, illuminating the origins of the cosmos, the nature of matter, and the fundamental rules governing reality itself. Through the interplay of quarks and leptons, the gradual cooling of the primordial soup, the explosive births and deaths of stars, and the powerful collisions within particle accelerators, the universe's grand narrative unfolds. It is a story of transformation and emergence, from the tiniest subatomic particles to the vast cosmic structures that frame our existence. Each step in this cosmic journey, governed by fundamental forces and intricate interactions, lays the foundation for the complexity and beauty that surrounds us, inviting us to explore deeper and marvel at the profound mysteries of the universe. Additionally, particle accelerators have played an essential role in exploring and testing some of the most profound theories about the early universe. These incredible machines accelerate particles to extraordinarily high speeds and smash them together, recreating conditions that are remarkably similar to those that existed mere moments after the Big Bang. Through these high-energy collisions, scientists have been able to investigate the existence of elusive particles such as various types of Higgs bosons, exotic mesons, and even subtle clues that may point towards the mysterious nature of dark matter. By carefully comparing the experimental outcomes from these particle collisions with the predictions generated by advanced theoretical models, physicists gain the ability to either validate or challenge our current understanding of the universe's origin, evolution, and the fundamental laws that govern it. In this sense, particle accelerators function almost like time machines, allowing humanity to peer back into the earliest moments of the cosmos and witness the fundamental processes that have shaped everything around us. Each experiment conducted within these accelerators helps to unravel more about how the tiniest constituents of matter formed and interacted in the dawn of time, crafting a progressively richer and more intricate story of the universe's beginnings. Imagine the earliest instance following the Big Bang. The universe was unimaginably hot and dense, a vast expanse filled with an intense sea of energy and fundamental particles zipping around at nearly the speed of light. As this primal universe expanded, it began to cool, setting the stage for the very first atoms to emerge. This cooling process was critical because it allowed fundamental particles, primarily protons and neutrons, to join together in a process known as nucleosynthesis. During this phase, which happened just minutes after the Big Bang, protons, which are essentially the building blocks of hydrogen, began pairing with neutrons. As temperatures dropped enough, these protons attracted electrons, forming the very first hydrogen atoms. Meanwhile, the remaining neutrons grouped to create helium nuclei, one of the simplest and most abundant elements in the universe. In those earliest moments, the cosmic recipe was roughly 3 hydrogen atoms for every helium atom. This primordial mixture laid the foundational groundwork for all the matter we observe today. Over billions of years, these hydrogen and helium atoms, drawn together by the inexorable pull of gravity, coalesce to form stars, galaxies, and the vast, intricate cosmic web that stretches across the observable universe. The initial formation of hydrogen and helium marked not only the birth of matter as we know it, but also the crucial starting point for the chemical complexity that would later develop in the cosmos. The young universe was initially devoid of heavier elements, those essential building blocks that allow for the existence of planets, life, and everything we recognize as complex matter. The story of heavier elements begins inside stars, where a remarkable process called nuclear fusion unfolds. Within the cores of stars, intense gravitational pressure generates blistering temperatures, allowing hydrogen atoms to collide and fuse into helium. This fusion reaction releases vast quantities of energy, the source of the dazzling light and heat that stars emit. As stars evolve, their internal structures undergo significant transformations. Once a star exhausts its hydrogen fuel, particularly in more massive stars, its core contracts and heats further, triggering fusion of helium into heavier elements such as carbon and oxygen. This ongoing cycle of fusion continues, enabling stars to produce progressively heavier elements, up to iron. Iron marks a critical boundary because fusing iron nuclei does not release energy, halting the fusion process that powers the star. When massive stars reach the end of their life cycles, they often culminate in spectacular explosions known as supernovae. These powerful events scatter the heavy elements forged during the star's lifetime into the surrounding cosmos. More than just dispersing existing elements, supernovae generate extreme environments ideal for the creation of even heavier atoms through a process called rapid neutron capture. In this phenomenon, free neutrons slam into existing atoms, which absorb these neutrons and undergo beta decay, transforming into new, heavier elements such as gold, uranium, and other rare materials. The debris from these stellar explosions enriches the interstellar medium with a diverse array of elements, which over time become incorporated into new stars, planets, and ultimately the very building blocks of life. Through this intricate cosmic dance of stellar evolution and cataclysmic explosions, the universe continually synthesizes the elements essential for creating everything from rocky planets to living organisms. Stellar nucleosynthesis, the process by which stars forge new elements, remains one of the most fascinating and vital mechanisms behind the diversity of matter we observe today. Consider a star's life as a transformative journey beginning with predominantly hydrogen atoms. Deep within its core, immense heat and pressure force hydrogen nuclei to combine into helium through a sequence of fusion reactions. This process releases tremendous amounts of energy, which manifests as the radiant light and warmth stars provide. As the star ages, it progresses through stages where different fusion reactions dominate. Once the star exhausts its hydrogen supply, it begins fusing helium into heavier elements like carbon and oxygen, a process that not only generates new materials, but also paves the way for the creation of even heavier elements as the star continues its life cycle. Ultimately, when stars reach the dramatic finale of their existence, especially in the form of supernova explosions, they liberate the elements they forged, spreading them throughout the cosmos. These explosions provide the energy and conditions necessary for the synthesis of elements heavier than iron via rapid neutron capture. With each successive generation of stars, a wider variety of elements is formed and dispersed across the universe. This continual enrichment of the interstellar medium supplies the essential materials for the formation of new stars, planets, and the emergence of life itself. Every atom in our bodies heavier than hydrogen has its origins in the fiery crucibles of ancient stars, revealing a profound connection between stellar processes and our own existence. Understanding stellar nucleosynthesis offers a clearer window into the ongoing evolution of the universe. It explains not only how stars live and die, but also how the elemental diversity needed for complex structures and life arises from the simplest primordial beginnings. The cosmic narrative etched in the elements around us tells a story of transformation, connection, and the relentless creative power of the universe itself. Supernovae play an absolutely vital role in the grand cosmic saga, acting as colossal stellar factories where the elements essential to the universe's makeup are both forged and dispersed. When a massive star reaches the twilight of its existence, it undergoes a cataclysmic explosion known as a supernova, an event so immense and powerful that it outshines entire galaxies for a brief moment in time. Yet this explosion is not merely a dazzling spectacle of light. It marks a critical phase in the cosmic life cycle, a turning point in how elements are created and scattered across the vastness of space. Throughout the lifespan of a star, nuclear fusion reactions occur deep within its core, where extreme pressures and temperatures enable lighter elements to merge and form heavier ones. Initially, hydrogen atoms fuse to form helium, releasing vast amounts of energy that sustain the star's brilliance. As the star ages, the fusion process advances to create progressively heavier elements. Helium fuses into carbon, carbon into oxygen, and this sequence continues, building up an impressive periodic table of elements inside the stellar core. Elements that include silicon, sulfur, and eventually iron. However, this fusion process hits a critical limit at iron because fusing iron requires more energy than it releases, causing the star's core to destabilize. It is precisely during the final moments when the star undergoes its supernova explosion that elements heavier than iron are synthesized. The extreme environment generated by the explosion, where temperatures soar to billions of degrees and pressures are unimaginably intense, enables rapid neutron capture processes that create precious and rare elements such as gold, silver, platinum, and uranium. These newly minted elements are violently expelled into the surrounding interstellar medium, effectively scattering the cosmic seeds necessary for future star systems and planets to form. This expelled material from supernovae enriches the cosmic environment with a rich mixture of elements and compounds, acting as a kind of universal fertilizer that contributes to the formation of new generations of stars, planets, and eventually life-bearing worlds. In essence, each supernova explosion distributes the fundamental building blocks for cosmic evolution across the galaxy, spreading the raw materials for complex chemistry and biology to take root. It is as though the universe is constantly engaged in a vast, ongoing process of cosmic cooking, where supernovae sprinkle the essential ingredients across the galaxy, allowing fresh celestial bodies to emerge from the enriched interstellar medium. Moreover, the remnants of supernova explosions, the gas and cosmic dust left behind, play an indispensable role in shaping the future architecture of star systems. This dust and gas act as the foundational building blocks for new stars and planetary systems, feeding the endless cycle of cosmic birth, death, and rebirth. Far from being mere endpoints, supernovae are central to the continuous evolution of the universe. They enrich space with the very elements that compose planets, the molecules that spark chemistry, and ultimately, the molecules essential to life as we know it, including ourselves. At the heart of this cosmic narrative lies the crucial role of chemical reactions. These reactions are the fundamental processes that enabled the universe to transform from its primordial simplicity into the richly structured cosmos we observe today. In the moments following the Big Bang, the universe was an unimaginably hot and dense expanse filled mainly with hydrogen and helium, the lightest elements. Over time, these elements began to interact through a complex network of chemical reactions and physical processes, causing clouds of gas to collapse under gravity's pull. As these gaseous clouds condensed, the pressure and heat ignited nuclear fusion within their cores, leading to the birth of stars. Inside these stellar furnaces, fusion reactions generated heavier elements, first converting hydrogen into helium, then helium into carbon and oxygen, setting the stage for the chemical complexity necessary for planetary formation. As massive stars reached the ends of their lives and exploded as supernova, they dispersed these elements throughout the cosmos, seeding the environment with the raw materials for the next generation of stars and planets. This dispersal created fertile cosmic nurseries where new chemical reactions could occur, allowing gases and dust to coalesce and form intricate molecular structures. On Earth, as conditions gradually stabilized, chemical elements began to combine in increasingly complex ways. These chemical reactions led to the emergence of simple organic molecules, the foundational building blocks of life. Over time, these organic compounds formed more complex structures capable of self-replication, eventually giving rise to living organisms. The continuous interplay of chemical reactions within the primordial environment was essential for life's emergence, and this chemical evolution has continued to unfold, leading to the remarkable diversity of life forms present today. The ongoing cycles of chemical transformations in Earth's atmosphere, oceans, and living organisms illustrate how chemical reactions underpin not only biological processes, but also geological and astronomical phenomena. These reactions form the basis of interactions within ecosystems and enable the formation of complex molecules such as DNA, proteins, and cellular structures that sustain life. The universe, in its vast complexity, is a grand symphony of chemical interactions where every reaction contributes to the unfolding story of existence, bridging the gulf between the simplest atoms and the intricate life forms that inhabit our planet. Turning now to the concept of nothingness, especially in the context of cosmology and physics, it reveals itself to be far more complex than everyday understanding suggests. In our daily lives, nothing is often equated with an absence, a vacant room devoid of objects or people, a blank space lacking matter. However, from a scientific perspective, nothing is not merely an empty void. Instead, it refers to the vacuum of space that, while devoid of conventional matter, is far from being devoid of activity. Quantum mechanics reveals that even a perfect vacuum is alive with dynamic fluctuations. Particles can spontaneously appear and disappear in an ongoing dance governed by the principles of uncertainty. These ephemeral particles, known as virtual particles, pop in and out of existence so rapidly that their presence cannot be directly observed, but their effects can be measured, revealing an energetic foam beneath the surface of what we perceive as empty space. This quantum foam challenges our intuition by showing that nothing at the fundamental level is a seething ocean of potential energy and activity. This insight raises profound philosophical and scientific questions about the nature of existence and the meaning of nothing. If a vacuum is never truly empty, then the concept of absolute nothingness may be an illusion. Instead, the vacuum becomes a dynamic landscape filled with energy and possibility, a fertile ground from which the universe itself might have emerged. Indeed, many cosmological theories propose that the universe began from a quantum vacuum state, a highly energetic condition teeming with potentiality from which space, time, and matter spontaneously arose. Further illustrating the complexity of nothingness, quantum vacuum fluctuations manifest in observable phenomena such as the Casimir effect, where two uncharged metal plates placed extremely close together in a vacuum experience an attractive force caused by these fluctuations. This effect not only demonstrates the physical reality of vacuum fluctuations, but also highlights the subtle interplay between quantum mechanics and classical physics. The scientific reinterpretation of nothingness transforms our understanding of the cosmos. What appears as emptiness is in fact a vibrant, dynamic state, brimming with unseen processes that defy conventional notions of a void. This challenges us to rethink the boundaries of existence and the origin of reality itself. Moving from the nature of emptiness to the origins of the universe, the theory of cosmic inflation offers a compelling explanation for the universe's earliest moments. According to this theory, immediately after the Big Bang, the universe underwent an extraordinarily rapid expansion, much like a balloon being inflated, but expanding exponentially faster in a tiny fraction of a second. This inflationary period smoothed out irregularities and homogenized the distribution of energy and matter, setting the initial conditions for the large-scale uniformity we observe today. During this rapid inflation, regions of space that were once in close contact became dramatically separated, like explaining why distant parts of the universe share similar temperatures and structural properties despite their immense distances apart. This theory provides a framework for understanding how the universe evolved from an extremely hot and dense state into the vast, structured cosmos we observe, with galaxies, stars, and planets scattered across incomprehensible distances. In summary, supernovae act as cosmic forges, crafting and dispersing the elements essential to life and planetary formation. Chemical reactions weave the complex tapestry of matter and life throughout the universe. Nothingness at the quantum level is a vibrant, dynamic state full of unseen energy and activity. And cosmic inflation explains the remarkable uniformity and scale of the universe's earliest expansion. Together, these profound phenomena compose the intricate and awe-inspiring story of the cosmos, a narrative of creation, transformation, and endless possibility. Cosmic inflation stands as one of the most profound breakthroughs in our understanding of the universe's earliest moments, addressing some of the most puzzling mysteries about how everything began. Imagine the universe just after the Big Bang, a chaotic, dense, hot environment. Inflation proposes that within an incredibly brief fraction of a second, the universe underwent an explosive and almost unimaginable expansion. Picture a tiny balloon rapidly inflating to a size so vast that the distances between points in space were stretched beyond what was previously possible. This sudden ballooning did not happen slowly or gradually. It was an extreme and rapid event, exponentially increasing the scale of the cosmos. This rapid expansion offers explanations for why, when we look out into the cosmos today, the universe appears so flat and remarkably uniform. Without inflation, the universe's large-scale flatness and homogeneity, meaning that space looks mostly the same in all directions, would be an extraordinary coincidence. But with inflation, regions that were once minuscule and tightly packed could be stretched out evenly across enormous distances, smoothing out any initial irregularities. The cosmic microwave background radiation, the faint glow left over from the Big Bang, is one of the most compelling pieces of evidence supporting this. This radiation is incredibly uniform, with only tiny fluctuations scattered throughout, perfectly consistent with the predictions of inflationary theory. But the story does not end there. Inflation also gives us a window into how the intricate cosmic web of galaxies, galaxy clusters, and vast voids began to form. The key lies in the quantum fluctuations, minute, random variations in energy and density that existed even in the universe's earliest moments. Though tiny, these fluctuations became stretched out and magnified by inflation. Over billions of years, gravity amplified these tiny ripples in density, turning them into the rich tapestry of stars, galaxies, and planetary systems we see scattered across the universe today. Without inflation providing this mechanism, the origin of the universe's large-scale structure would remain a profound enigma. Quantum fluctuations themselves reveal an astonishing aspect of reality. When we think of nothing, the common assumption is that it means a total absence of anything, no matter, no energy, no activity. However, quantum physics radically challenges this notion. The vacuum, or what we traditionally imagine as empty space, is far from empty. Instead, it is a roiling sea of potential, a bubbling cauldron where particles and energy spontaneously appear and vanish in the blink of an eye. These ephemeral appearances are not permanent. Virtual particles flicker in and out of existence, so fleeting that we cannot directly observe them. Their presence is like waves rising and falling in a turbulent ocean, constantly reshaping the fabric of what we call empty space. This dynamic activity stems from the uncertainty principle, a cornerstone of quantum mechanics that limits how precisely we can measure energy and time simultaneously. Because of this fundamental uncertainty, the vacuum becomes a place where energy can briefly borrow existence, creating particles for mere fractions of a second before they vanish again. These virtual particles are not just theoretical curiosities, they have tangible effects. One striking example is the Casimir effect, where two closely spaced uncharged metal plates in a vacuum attract each other due to the pressure exerted by these virtual particles. This phenomenon demonstrates that even what appears to be the emptiest parts of space harbor a subtle, restless energy shaping the physical world. These quantum fluctuations are not merely small-scale oddities. Some cosmologists theorize that the entire universe's birth, the Big Bang itself, could have been triggered by such fluctuations in this primordial quantum vacuum. The transition from this energetic nothing into everything we know could be seen as the moment when the cosmos emerged from a dynamic and fluctuating state into a vast and evolving universe. When we take a step back and consider the entire picture, cosmic inflation and quantum fluctuations together provide a powerful framework for understanding how the universe evolved from a near-featureless, chaotic beginning to the magnificent complexity we observe today. Inflation describes the rapid, expansive phase that stretched the fabric of space, setting the stage for structure formation, while quantum fluctuations seed the density variations that gravity would later sculpt into stars, galaxies, and planets. This dual process transforms our understanding of nothing itself, from an empty void to a vibrant source of possibility, where the fundamental laws of physics dance with chance and probability to create all that exists. The universe, in essence, tells a story of transformation. From the quantum vacuum's restless energy and bubbling virtual particles to the massive inflationary burst that expanded space-time itself, these phenomena are the foundation stones of cosmic history. They reveal a universe not born out of static emptiness, but from a dynamic and fertile field of potential, shaping everything from the smallest subatomic particles to the grandest galactic superclusters. Every star, every planet, every living being, including ourselves, owes its existence to these profound early moments when nothing became something, and the cosmos began its vast and ongoing journey. Additionally, researchers have dedicated extensive efforts to studying gravitational waves generated during the universe's inflationary period. These waves, ripples in the very fabric of space-time, hold the promise of unlocking deep secrets about the universe's earliest moments. Although direct detection of these primordial gravitational waves remains a monumental challenge still underway, their eventual discovery would serve as a groundbreaking confirmation of the inflationary theory. This theory posits that the universe underwent a brief but extraordinarily rapid expansion just fractions of a second after the Big Bang. Detecting these waves would illuminate conditions at the very dawn of existence, revealing a snapshot of cosmic history that has so far eluded direct observation. Delving deeper into this cosmic puzzle, scientists have also examined the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. This faint, pervasive glow blankets the entire sky and carries within it delicate imprints from the universe's infancy. Acting like a fossil record etched across space and time, the radiation preserves the subtle fingerprints of that early rapid expansion, reinforcing the validity of the inflationary model. When these disparate lines of evidence are woven together, the inflation theory emerges as a compelling framework. It elegantly explains many observed properties of the cosmos, bridging our understanding from a universe that began in a nearly uniform and unimaginably hot state to the complex tapestry of galaxies, stars, and structures visible today. The inflationary theory offers a fascinating explanation for the remarkable uniformity we observe in the cosmic microwave background radiation. This radiation, a faint but steady glow permeating the entire universe, acts as a snapshot of the cosmos during its formative moments, revealing temperatures that are surprisingly consistent across vast expanses of space. To visualize this, imagine the universe just moments after the Big Bang, when it was incredibly hot and dense beyond comprehension. According to the inflation hypothesis, during the first instance of its existence, the universe expanded exponentially, a swift and dramatic ballooning in size. This expansion happened so quickly that regions initially close together were flung far apart almost instantaneously. Amid this explosive growth, minute fluctuations in energy dispersed throughout the cosmos. These tiny ripples, representing slight variations in density, might have seemed insignificant at the time, but they would have profound consequences. As the universe continued to expand and cool over billions of years, these small differences in density seeded the formation of galaxies and large-scale cosmic structures. The universe's eventual architecture, the clusters of galaxies, vast filaments, and immense voids, traces its origins back to these primordial fluctuations. Interestingly, the striking uniformity of the cosmic microwave background radiation arises because regions of the universe that were once in close proximity had the chance to reach thermal equilibrium before being rapidly separated during inflation. This means that even though these regions are now separated by billions of light years, they share nearly identical temperatures because they once interacted and exchanged energy. Inflation provided the stage for this large-scale homogeneity, ensuring the universe began with similar initial conditions. This, in turn, explains why the cosmic microwave background appears so smooth and uniform, despite the complex structures that developed later. The concept of an expanding universe carries profound implications for its future. Picture the cosmos as a gigantic balloon being steadily inflated. As it expands, galaxies move away from each other, akin to dots on the surface of a balloon stretching farther apart. This expansion is not a fleeting phenomenon, but a fundamental feature of the universe itself. One of the most significant consequences of this ongoing expansion is the gradual separation of galaxies. Over time, the gravitational forces that once held galaxies and clusters together may be insufficient to counter the increasing distances. Eventually, galaxies could become isolated, drifting apart into vast cosmic voids, creating a lonely, sparsely populated universe. Adding a further layer of complexity, the expansion of the universe is accelerating, a discovery that has transformed our understanding of cosmology in recent decades. This acceleration suggests the presence of a mysterious and invisible form of energy known as dark energy, which drives this cosmic speed-up. Dark energy remains one of the greatest enigmas in modern astrophysics. Its true nature is still unknown, but its effects are clearly observable through the accelerated expansion. If this acceleration persists, it could culminate in a scenario often called the Big Freeze. In this distant future, stars will have exhausted their nuclear fuel, leaving behind a cold, dark universe where star formation ceases entirely and existing stars slowly fade away. Even more dramatic is the possibility of a Big Rip, a catastrophic end where the expansion of the universe becomes so intense that it tears apart galaxies, stars, planets, and ultimately the very atoms themselves. This apocalyptic vision would arise if the forces driving expansion, namely dark energy, become dominant over all gravitational attraction, ripping apart the fundamental structures that compose the cosmos. Thus, the ongoing expansion of the universe paints a picture of a future that starkly contrasts with the vibrant and energetic cosmos we inhabit today. Over unimaginable stretches of time, the universe may drift into isolation and darkness, raising profound questions about the ultimate fate of existence and our place within the vast, ever-evolving cosmic arena. Tracing the narrative of the universe's expansion inevitably leads back to the Big Bang, the defining event marking the beginning of everything. From this singular origin, the universe initially expanded rapidly, undergoing a phase known as inflation. During this period, it ballooned exponentially in size within an incredibly short fraction of a second. At this time, the universe was suffused with energy, intensely hot and expanding at an astonishing pace. The very fabric of space itself stretched, setting the foundational conditions for the universe's subsequent evolution. As time marched on, the initially furious pace of expansion began to slow, primarily due to the gravitational pull exerted by matter accumulating within the cosmos. This phenomenon can be likened to blowing up a balloon. At first, the air pressure inside pushes outward with great force, causing rapid expansion. But as the balloon grows larger, inflating it further requires increasingly more effort because the elastic resistance increases. Similarly, the early rapid expansion of the universe eventually encountered resistance as gravity, pulling on the growing clumps of matter, began to slow the rate of expansion. This interplay between expansion and gravity has profoundly shaped the universe's history. While inflation created the large-scale uniformity and spread matter thinly across enormous volumes, gravity's pull fostered the formation of stars, galaxies, and the intricate web-like cosmic structures that define the observable universe. From the earliest moments of explosive growth to the gradual assembly of complex systems, the universe's expansion tells a story of dynamic forces interacting across billions of years, a story that continues to unfold with every passing moment. However, something truly extraordinary occurred about 5 billion years ago that changed the course of the universe's expansion in a way that continues to captivate scientists and observers alike. After billions of years of slowing down due to the gravitational pull of matter, stars, galaxies, and the unseen dark matter holding them together, the universe's rate of expansion began to increase once again. This unexpected acceleration is attributed to a mysterious and elusive force known as dark energy, a phenomenon that challenges our fundamental understanding of physics and the cosmos. Dark energy is unlike any force or influence we experience in everyday life. While gravity is a familiar attraction that pulls objects toward each other, dark energy acts in the opposite manner. It pushes, drives, and propels galaxies further apart, creating a cosmic tug-of-war on an unimaginable scale. Imagine an invisible hand continuously pressing outward on the fabric of space itself, accelerating the universe's expansion, instead of allowing it to slow under gravity's influence. This mysterious force operates uniformly across the vastness of space, with a repulsive effect that overwhelms the attractive pull of gravity between distant galaxies. Tracing the universe's expansion history reveals a remarkable story. Immediately after the Big Bang, the universe underwent an extraordinarily rapid inflationary period, during which space expanded at an almost unimaginable speed. This early burst of inflation smoothed and stretched the cosmos, setting the stage for everything that followed. After this brief, furious expansion, the universe entered a phase where its growth slowed down significantly. Gravity, pulling matter together, was the dominant force, gradually decelerating the expansion rate. This epoch lasted billions of years and led to the formation of the large-scale structures we observe today: galaxies, clusters of galaxies, and vast cosmic webs connecting them. Yet, around 5 billion years ago, the cosmic narrative shifted dramatically. Observations made by astronomers in the late 20th century revealed that the expansion was not only continuing but accelerating, defying all prior expectations. This puzzling phenomenon forced scientists to introduce the concept of dark energy, an unseen, pervasive form of energy that fills the vacuum of space and exerts a repulsive force strong enough to overpower gravity at large scales. Today, dark energy is believed to make up approximately 70% of the universe's total energy content, dominating over ordinary matter and dark matter combined. To understand the role of dark energy, it helps to visualize the universe as an enormous balloon being inflated. When you blow air into a balloon, the surface stretches and points on the surface move away from each other uniformly in all directions. Similarly, the universe's space itself is expanding, causing galaxies to drift apart as if embedded on the surface of an ever-growing balloon. Initially, the gravitational pull of matter slowed this expansion, akin to someone gently pressing their hands against the balloon to slow its inflation. But dark energy acts like an unseen force, releasing that pressure and then pushing the balloon outward faster and faster. The nature of dark energy remains one of the greatest mysteries in modern cosmology. Scientists have many hypotheses, but no definitive answers. Some propose that dark energy is a fundamental property of space itself, known as the cosmological constant, a concept originally introduced by Albert Einstein but later discarded, only to be revived by modern observations. Others suggest dark energy might represent a new, dynamic field with changing strength over time, or that it could signal the need for entirely new physics beyond our current theories. Despite these uncertainties, dark energy has revolutionized our understanding of the cosmos, revealing a universe far more complex and strange than previously imagined. The ongoing cosmic tug-of-war between the attractive force of gravity and the repulsive push of dark energy determines the ultimate fate of the universe. If dark energy's influence continues to grow stronger, the universe will expand forever, galaxies moving ever farther apart, stars burning out, and the cosmos growing colder and darker in a distant future, sometimes called the Big Freeze. Alternatively, if dark energy's effects change or weaken, the expansion might slow down or even reverse, potentially leading to a big crunch, where all matter collapses back together. Another possibility is that the universe could reach a steady state, with expansion slowing to a stable rate. Each of these scenarios poses profound questions about the nature of reality and the destiny of everything within it. Long before this accelerating expansion began, the universe's earliest moments tell their own incredible story. Shortly after the Big Bang, the cosmos was a hot, dense, and nearly uniform cloud of primordial matter composed mainly of hydrogen and helium atoms, along with a sea of subatomic particles. As the universe expanded, it cooled down and the energy available to these particles decreased. Gravity began to play its crucial role, pulling together tiny fluctuations in the otherwise smooth matter distribution. Imagine tiny dust motes in a sunbeam slowly gathering into larger clumps. These small irregularities in density grew over time, forming gravitational wells that attracted more and more matter. These gravitational wells deepened as they pulled in hydrogen and helium gas, eventually reaching densities sufficient to ignite the first stars. These earliest stars, often called population 3 stars, were massive and short-lived, blazing brilliantly before exploding in powerful supernovae that seeded the cosmos with heavier elements necessary for the formation of planets and life. Groups of these stars gathered together to form the first galaxies, cosmic islands of light scattered across the vast darkness. Within these galaxies, the cycle of star birth and death continued, enriching the interstellar medium with heavier elements and shaping the cosmic environment. Galaxies themselves did not remain isolated. Over billions of years, they interacted through gravity, merging with one another to form larger and more complex structures. This cosmic evolution led to the intricate web of galaxies, clusters, and superclusters we observe today, interconnected by vast filaments of dark matter and separated by enormous voids. This grand architecture reflects the deep interplay between gravity, dark matter, and the mysterious influence of dark energy. In this ongoing cosmic drama, dark energy is the most enigmatic character. Its invisible presence drives the universe's expansion faster and faster, stretching the cosmic fabric beyond what gravity alone could achieve. The universe's expansion is not merely a passive stretching, but a dynamic, evolving process shaped by forces we are only beginning to comprehend. The future of the cosmos depends on how these forces will interact over unimaginable timescales, guiding the destiny of galaxies, stars, planets, and perhaps life itself. Thus, the journey of the universe from its fiery birth to its accelerating expansion today reveals a story of transformation, mystery, and awe. Each discovery about dark energy, cosmic expansion, and the formation of galaxies deepens our understanding while opening new frontiers for exploration. The universe is a vast, ever-changing tapestry woven from the threads of matter, energy, and space-time, with dark energy as a hidden force pushing it toward an uncertain but fascinating future. As galaxies took their first tentative steps in the early universe, they did not evolve in isolation. Instead, they began to gather in ever larger and more complex assemblies known as clusters and superclusters, immense congregations of galaxies held tightly together by the invisible but powerful force of gravity. These grand cosmic structures did not appear randomly, but emerged from subtle variations in the density of matter present in the primordial universe, long before stars or galaxies had even formed. Imagine, if you will, a vast cake with icing spread unevenly across its surface, some areas thicker and richer than others. Those slightly denser regions in the early cosmic soup acted as gravitational wells, attracting surrounding matter and seeding the formation of the universe's large-scale framework. Over billions of years, these variations in density transformed the cosmos from a nearly uniform expanse into a richly textured tapestry of galaxies woven together in a colossal cosmic web. This web, stretching across unimaginable distances, consists of filaments composed largely of dark matter, a mysterious, invisible substance that exerts gravitational pull yet eludes direct detection. Through these filaments, countless galaxies are connected, forming a complex network that defines the architecture of the observable universe. The journey from an initial, smooth state to this intricate cosmic structure is a testament to the persistent and patient work of gravity acting under the laws of physics. Gravity, the fundamental force that governs the motions of celestial bodies, has been the universe's master architect since the moments immediately following the Big Bang. In those earliest times, the universe was a hot, dense plasma of particles, constantly expanding and cooling. As it expanded, the subtle fluctuations in density allowed gravity to begin pulling matter together, much like an invisible magnet drawing actors on a stage toward one another. These gravitational gatherings gave birth to the first stars and galaxies, igniting the cosmic dawn. As these nascent structures formed, their gravitational influence grew stronger, drawing in more gas, dust, and the elusive dark matter. This cycle of accumulation and growth continued relentlessly, sculpting the vast cosmic landscape seen today. Galaxies became the fundamental building blocks, assembling into groups, clusters, and superclusters, their shapes and dynamics constantly influenced by gravity's unyielding grip. This force not only shaped the formation of these structures, but also dictated their ongoing evolution. Galaxies collided, merged, and transformed, their stars redistributed in complex dances that spanned millions of years. The movements of stars within galaxies, the interactions between galaxies themselves, and the grand-scale collisions of clusters all bear gravity's unmistakable mark. Stars orbit within their galactic homes, bound by gravitational forces that maintain the structural integrity of these immense stellar cities. At the same time, gravity governs the motions and encounters of celestial bodies on scales ranging from tiny star systems to vast galaxy superclusters, orchestrating an ever-changing cosmic ballet that continues unabated. To unravel the mysteries of this grand cosmic evolution, scientists rely on sophisticated simulations and computational models. These virtual universes allow researchers to recreate the intricate dance of matter and gravity over billions of years, providing a window into processes impossible to observe directly. By inputting initial conditions derived from astronomical observations, such as the distribution of dark matter and ordinary gas, these simulations become powerful laboratories where the complex dynamics of galaxy formation and evolution can be studied. Within these digital realms, galaxies collide and merge. Star formation ignites and fades, and the influence of gravity shapes every interaction. By adjusting parameters like galactic mass or star formation rates, scientists explore countless hypothetical scenarios, testing what-if questions that reveal the range of cosmic possibilities. These models offer crucial insights, helping to interpret observations and refine our understanding of the universe's past, present, and future. One of the most dramatic and transformative processes in the cosmic narrative is the collision and merger of galaxies and larger structures. Picture the universe as an immense living tapestry, with each thread representing a galaxy or cluster. When these threads intertwine in collisions, they do not merely alter individual galaxies, but reshape the very fabric of the cosmos itself. The force driving these transformations is gravity, pulling vast quantities of matter together with irresistible strength. As galaxies draw near each other, their gravitational fields interact, distorting their shapes and triggering tidal forces that can stretch and warp their stellar and gaseous components. These encounters often ignite intense bursts of star formation, creating stellar nurseries where countless new stars blaze into existence. This renewal invigorates the surrounding regions, contributing to the evolving cosmic landscape. But galaxy collisions do more than spark creation. They rearrange the stars already present. During mergers, stars can be flung into new orbits or even ejected entirely into the vast emptiness of intergalactic space. This redistribution reshapes galaxies, transforming smaller primitive forms into vast spirals or enormous elliptical giants. On an even grander scale, when entire clusters of galaxies collide, the consequences ripple across intergalactic space. The colossal shockwaves unleashed in these encounters travel through clouds of hot gas permeating the spaces between galaxies, heating them to extraordinary temperatures. These shockwaves influence the formation of new stars, sometimes igniting cosmic phenomena of immense power, such as supernova explosions, while contributing to the formation of complex flex filaments stretching across the universe. These filaments, in turn, serve as highways along which galaxies and matter flow, feeding the ongoing evolution of the cosmic web. From the subtle early variations in matter density to the titanic collisions of galaxy clusters, the story of the universe's large-scale structure is one of gravity's enduring influence, shaping and reshaping the cosmos over billions of years. This story is still unfolding, observed by ever more powerful telescopes and explored through ever more sophisticated simulations, offering humanity a glimpse into the majestic and intricate workings of the universe on its grandest scales. Moreover, these vast cosmic interactions hold immense significance for the grand design of the universe. As colossal structures drift through space and inevitably collide and merge, the large-scale arrangement of the cosmos grows ever more refined and ordered. What once appeared as a tangled, chaotic web composed of smaller clusters and slender filaments gradually transforms into an intricate hierarchical framework. In this evolving architecture, enormous galaxy clusters rise as dominant features, surrounded by smaller groups of galaxies and immense cosmic voids that stretch across unimaginable distances. Collisions and mergers between these structures serve as the universe's very own sculpting instruments. Like master artisans, these dynamic forces chip away at older cosmic forms, breaking them down and reshaping them, giving birth to entirely new configurations. This process drives the continuous evolution of galaxies, enriching the interstellar medium, the vast spaces between stars, with heavier elements. These elements are forged in the fiery furnaces of stellar explosions, events that scatter complex atoms across galaxies. In doing so, such cosmic encounters lay the foundational groundwork for future generations of stars and galaxies, fueling a cycle of creation and transformation that has persisted for billions of years. By delving into the nature of these cosmic encounters, humanity gains invaluable insights into the universe's own history and ongoing evolution. When astronomers observe distant galaxies, they essentially peer back in time, catching glimpses of the universe as it was billions of years ago. The light traveling from these remote galaxies to Earth requires vast spans of time, sometimes billions of years, to reach us. This means that when we observe these galaxies, we are witnessing them as they existed in epochs long past, each one representing a snapshot, capturing a different stage of cosmic evolution. This celestial time travel allows scientists to study the formation and development of galaxies across vast stretches of cosmic history. By carefully analyzing the light emitted by these distant galaxies, astronomers assess their composition, structure, and behavior. Through this analysis, they can deduce crucial properties such as the galaxy's age, their distance from Earth, and their movement through space. Such data is essential for understanding how the universe itself expands and evolves. This process unveils the grand narrative of cosmic history following the Big Bang, revealing how the first stars and galaxies formed from primordial gases. Early galaxies hold vital clues about the types of elements present shortly after the Big Bang and illuminate the mechanisms by which simple gases transformed into the complex, structured universe we observe today. Observations further disclose how galaxies interacted, merged, and influenced one another over time, helping to construct a comprehensive and vivid picture of cosmic history. Studying these distant galaxies allows scientists to piece together the vast and intricate story of the universe, from its infancy to its current state. It offers profound insights into cosmic evolution, the development of matter, and the fundamental forces that have shaped every star, planet, and galaxy visible to us. Today, astronomers wield a unique power, the ability to explore the past by analyzing light from the farthest reaches of space. When we gaze up at the night sky, the light reaching our eyes has traveled unimaginable distances, often for millions or even billions of years. The farther away an object lies, the longer its light has taken to journey to us, effectively allowing us to look back in time. Consider a star located many light years away. The photons we see from this star today may have left its surface millions or billions of years ago. By studying this ancient light, astronomers can reconstruct details about the star's life, its chemical composition, and the cosmic environment that existed when the light was first emitted. Every flicker of light becomes a frozen moment in the vast timeline of cosmic history. This concept grows even more fascinating when applied to ancient cosmic phenomena, such as the birth of galaxies or the immediate aftermath of the Big Bang. Different wavelengths of light carry unique information about these events. For example, visible light reveals the stars themselves, while infrared light uncovers cooler objects like dust clouds or distant galaxies hidden behind cosmic curtains. Ultraviolet light, on the other hand, highlights energetic processes occurring in young stars and galaxies. Light traveling across the expanding universe experiences stretching, a phenomenon called redshift. As space itself expands, the wavelengths of light lengthen, shifting toward the red end of the spectrum. This redshift provides astronomers with a cosmic speedometer, allowing them to measure how rapidly galaxies move away from us and trace the universe's evolution over time. By assembling these observations, scientists craft a detailed timeline of cosmic events, offering deep insight into the origin and growth of the universe. Using light as a bridge to the past enriches our understanding of cosmic history and connects us to moments when the universe was still taking shape. To glimpse the universe's formative years, especially those immediately following the Big Bang, scientists rely on an array of sophisticated technologies. One of the most crucial tools in this endeavor is the powerful telescope. These instruments observe light across multiple wavelengths, including those invisible to the human eye. Many telescopes reside in space, far above Earth's atmosphere, to avoid atmospheric distortion. These space-based observatories can detect faint infrared and radio waves, revealing light emitted by some of the earliest stars and galaxies. Spectroscopy also plays a vital role in unraveling cosmic mysteries. By splitting light into its constituent colors, this technique allows scientists to determine the chemical composition, temperature, and distance of celestial objects. Such data are indispensable for understanding how stars formed and evolved throughout cosmic history. Moreover, advancements in measuring cosmic microwave background radiation are indispensable for peering back to the universe's infancy. This faint glow acts as a leftover signature from the earliest moments after the Big Bang, like a cosmic snapshot frozen in time. Instruments designed to detect this subtle radiation provide a window into conditions prevalent shortly after the universe began, helping to uncover the processes that led to the formation of the first cosmic structures. Through these collective efforts, observing distant galaxies, analyzing their light, and studying cosmic background radiation, scientists piece together the profound and awe-inspiring story of the universe's birth, growth, and continuous transformation. Each discovery adds new chapters to this cosmic saga, deepening humanity's connection to the universe and its timeless dance of creation and evolution. Moreover, computer simulations, fueled by highly sophisticated algorithms and immense processing power, play a pivotal role in helping scientists make sense of the overwhelming volumes of data collected from observations of the cosmos. These simulations serve as virtual laboratories where researchers recreate and examine the behavior of matter and energy in the universe's infancy, long before galaxies and stars fully formed. By running these complex models, scientists can bridge the sometimes significant gaps between theoretical predictions and the actual data gathered by telescopes and detectors, allowing a more complete understanding of cosmic phenomena that are otherwise impossible to witness directly. In recent years, a revolutionary advance in astronomy has come with the advent of gravitational wave detectors. These instruments can detect faint ripples in the very fabric of space-time caused by colossal cosmic events such as the collisions of black holes or neutron stars. These ripples, known as gravitational waves, carry information about events that happened in the earliest epochs of the universe, offering a brand new and independent way to study cosmic history. By capturing these subtle signals, gravitational wave astronomy opens an unprecedented window into the most violent and energetic processes in the cosmos, revealing interactions and collisions that light-based telescopes alone cannot observe. The combination of traditional electromagnetic observations with gravitational wave data forms an extraordinarily powerful toolkit pushing the boundaries of our knowledge deeper into the universe's past than ever before. These technologies, when combined with some of the most advanced telescopes humanity has ever built, create a comprehensive and multifaceted approach to exploring the origins and evolution of the cosmos. Among these telescopes, the Hubble Space Telescope and the James Webb Space Telescope stand out as monumental achievements in astronomical observation. Hubble, launched toward the end of the 20th century, has provided astonishingly clear images of distant galaxies, nebulae, and other celestial objects. Its ability to capture light emitted billions of years ago has been instrumental in reconstructing a timeline of the universe, offering crucial insights into how galaxies formed, grew, merged, and interacted over cosmic time. The clarity and depth of Hubble's images have allowed astronomers to trace the intricate history of star formation and cosmic structure formation throughout billions of years. In contrast, the James Webb Space Telescope, designed to observe predominantly in the infrared spectrum, has capabilities that complement and extend those of Hubble. Infrared light, with its longer wavelengths, can penetrate dense cosmic dust clouds that often obscure visible light. This allows James Webb to peer into stellar nurseries, regions where new stars and planets are actively being born, hidden behind veils of gas and dust. Its sophisticated instruments can analyze the chemical composition of distant stars and planetary systems, helping scientists uncover the makeup of their atmospheres and assess their potential for hosting life. The telescope's sensitivity and resolution enable deep exploration into the cores of distant galaxies, revealing processes related to star formation and the growth of supermassive black holes. By combining the data from these two telescopes, scientists build a richer, more nuanced picture of the universe's history, from the aftermath of the Big Bang to the complex galactic environments seen today. One of the fundamental tools astronomers use to understand the universe's expansion and its vast scale is the phenomenon known as redshift. Redshift occurs when the light emitted by an object in space is stretched to longer wavelengths, shifting it toward the red end of the electromagnetic spectrum. This effect is most famously linked to the expansion of the universe itself. To imagine this, picture the universe like a balloon being inflated. As the balloon expands, any 2 points on its surface move away from each other. Similarly, galaxies are drifting apart as space itself expands, and as they move farther from us, the light they emit stretches, causing that light to shift toward redder wavelengths. This shift is not merely a curiosity, but a crucial cosmic tool, allowing astronomers to measure the velocity at which celestial objects are receding and estimate their distance from Earth. The greater the red shift observed, the faster the object is moving away, giving important clues about the scale and rate of the universe's expansion. Redshift also serves as a cosmic time machine, letting scientists look back billions of years into the universe's history. Because light travels at a finite speed, observing distant galaxies means witnessing them as they were long ago. The farther away a galaxy is, the longer its light has taken to reach us. So by measuring redshift, astronomers piece together how the universe has changed over time. This method reveals not only how fast the universe is expanding, but also sheds light on its age and the fundamental forces driving its evolution. Without redshift, our understanding of cosmology would be vastly poorer, lacking the ability to trace the dynamic processes that have shaped the cosmos from its violent beginnings to the sprawling, structured universe we inhabit today. Despite the incredible advancements in technology and theory, scientists face immense challenges when attempting to collect accurate data about the universe's earliest moments. One of the most formidable obstacles stems from the extreme conditions of the early cosmos itself. Just after the Big Bang, the universe was an extraordinarily hot and dense environment, filled with high-energy radiation and matter in forms unlike anything we see today. The light and radiation emitted at that time have been stretched, redshifted, and scattered by billions of years of cosmic expansion, making direct observations difficult. This ancient light now exists mostly in wavelengths that are much harder to detect, such as microwaves or radio waves, requiring highly sensitive instruments capable of picking up these faint signals against a noisy background. Another challenge arises from the fact that we only see the universe as it is now, or as it appeared when the light we observe began its journey toward Earth. This situation is similar to attempting to reconstruct a vast jigsaw puzzle without ever seeing the completed picture. The universe is incredibly vast, and the finite speed of light means that the most distant cosmic events are seen only after billions of years of travel time. Interpreting these observations accurately demands a careful and complex understanding of astrophysics, combined with sophisticated models and simulations that help fill in missing pieces of the puzzle. Among the most significant relics from the early universe is the cosmic microwave background radiation. This faint glow, a remnant heat signature from the Big Bang, pervades all space and acts as a kind of cosmic fossil, preserving a snapshot of the universe when it was merely a few 100,000 years old. Capturing and analyzing this ancient radiation requires instruments of extraordinary precision and sensitivity. Scientists must distinguish the cosmic signal from numerous sources of interference and noise, both terrestrial and cosmic, that can obscure or distort these delicate measurements. The development of detectors and satellites capable of this feat has opened a window into the universe's infancy, providing invaluable data that informs our understanding of its birth and the fundamental physical laws governing its evolution. In summary, the combined efforts of cutting-edge computer simulations, revolutionary gravitational wave detectors, powerful space telescopes, and precise measurements of cosmic phenomena such as redshift and cosmic microwave background radiation collectively advance humanity's quest to unravel the universe's deepest secrets. Each technology contributes a unique perspective, and together they weave an ever more detailed and dynamic tapestry of cosmic history, revealing not only how the universe formed and evolved over billions of years, but also raising profound questions about our own place in this vast, mysterious expanse. Moreover, theories about the early universe delve deep into some of the most intricate and profound areas of physics, weaving together concepts that challenge even the most brilliant minds. At the core of these investigations lie two monumental pillars of modern science: quantum mechanics and general relativity. Quantum mechanics, which governs the behavior of particles at the smallest scales imaginable, and general relativity, which describes the curvature of space-time and the force of gravity on cosmic scales, must both be engaged to piece together the story of the universe's birth and its subsequent unfolding. Scientists are faced not only with the formidable task of gathering observational data from distant cosmic phenomena, but also with the challenge of interpreting these observations within the frameworks that these advanced theories provide. This task demands a delicate balance between theoretical predictions and empirical evidence, an interplay that is often fraught with complexity and uncertainty. The subtleties involved in reconciling predictions with what is observed can make the pursuit of definitive conclusions a profound challenge, requiring endless refinement of models and continuous reassessment of assumptions. As the frontiers of knowledge expand, there is an unceasing need for the development of cutting-edge technology and innovative methodologies. Instruments such as powerful space telescopes, which peer across vast stretches of time and space to collect faint light from the earliest galaxies, and highly sensitive particle detectors, which probe the fundamental constituents of matter, are indispensable tools in this scientific odyssey. Each leap in technological capability opens new windows into the universe's distant past, compelling researchers to constantly adapt their approaches and techniques to harness these advances effectively. This ongoing evolution of observational methods creates a dynamic and sometimes daunting landscape in cosmology, one that is as exciting as it is challenging. Within this landscape, researchers persist with relentless dedication, driven by the profound desire to unravel the mysteries that lie in the cosmic dawn. Gravity stands out as one of the fundamental forces that have shaped the universe since its very inception. In the chaotic moments following the Big Bang, the universe existed in a state of unimaginable heat and density. As it expanded and began to cool, minuscule fluctuations in density within this primordial plasma set the stage for all the cosmic structures we observe today. Gravity played a pivotal role in this grand cosmic drama by pulling matter toward regions of slightly higher density. This process of gravitational attraction caused particles and clumps of matter to coalesce, forming the first building blocks of structure. These growing clumps eventually led to the formation of stars and galaxies, the luminous beacons scattered across the night sky. Within stars themselves, gravity remains essential. It acts as the force compressing matter inward, counterbalanced by the outward pressure generated by nuclear fusion, the process that fuses lighter atomic nuclei into heavier ones, releasing vast amounts of energy in the process. This balance between gravitational collapse and fusion pressure defines the life cycles of stars, from their birth in nebulae to their ultimate fate. When a star exhausts its nuclear fuel, gravity once again takes over, pulling the star's remnants into incredibly dense objects such as neutron stars or black holes, depending on the original mass of the star. On even grander scales, gravity governs the intricate dance of galaxies within clusters. It dictates their movements, interactions, and collisions, which can trigger bursts of star formation and alter the distribution of dark matter, a mysterious and invisible form of mass that dominates the universe's overall content. Over billions of years, these gravitational interactions sculpt the large-scale structure of the cosmos, forming the vast cosmic web of filaments and voids that we observe through telescopes. Yet, gravity's influence is not the whole story when it comes to the expansion of the universe. While the initial momentum from the Big Bang propelled the cosmos outward, gravity acts to slow this expansion by pulling matter inward. Intriguingly, observations have revealed that the expansion of the universe is actually accelerating, a phenomenon attributed to a mysterious force called dark energy. This dynamic tug-of-war between gravity and dark energy continues to shape the universe's evolution today, influencing how galaxies form, how stars live and die, and the very architecture of the cosmic web. Despite being the weakest of the four fundamental forces, gravity's role is far from passive. It actively participates in the unfolding narrative of cosmic history, guiding the formation, growth, and transformation of celestial bodies and structures on every scale. While gravity dominates on astronomical scales, the other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, govern phenomena at the atomic and subatomic levels. Electromagnetism, for instance, controls the interactions between charged particles, determining how atoms bond together to form molecules, which then become the essential building blocks of all matter, including the stars, planets, and life itself. When gravity gathers atoms into dense clouds, electromagnetism ensures that these atoms can connect and react in ways that lead to the rich chemical complexity observed in the universe. The strong nuclear force operates within the heart of atomic nuclei, binding protons and neutrons together with tremendous strength. This force provides the stability necessary for stars to sustain nuclear fusion over millions or even billions of years. During the cataclysmic events of supernova explosions, gravity causes the collapse of massive stars under their own weight, pushing matter into realms of extreme density and pressure, where the limits of the strong force are tested to their utmost. In these extreme environments, gravity's influence can give rise to neutron stars, celestial objects so dense that their matter is compressed beyond the atomic level, or even black holes, where gravity's pull is so intense that not even light can escape. The weak nuclear force, although less widely known, plays a vital role in processes like certain types of radioactive decay and stellar fusion reactions. It facilitates the transformation of lighter elements into heavier ones within stars, enabling the synthesis of new elements that enrich the cosmos. This force allows the release of energy necessary to sustain the cycles of stellar birth, life, and death. In this cosmic interplay, gravity emerges as the dominant force orchestrating the grand cosmic symphony, while the other fundamental forces provide the fine details and nuances at the scale of particles and nuclei. Together, they weave the complex tapestry of phenomena that span from the birth of stars to their spectacular deaths, knitting the universe into the intricate and dynamic whole we observe. Throughout history, scientists have strived to understand these fundamental forces not as isolated phenomena, but as aspects of a unified framework. This quest for unification represents one of the most ambitious and profound endeavors in physics. Initially, the four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force were identified as distinct entities, each operating under specific conditions. However, underlying principles hinted at a deeper connection. A landmark breakthrough in this effort was the development of the Standard Model of Particle Physics, which successfully unified electromagnetism and the weak nuclear force into a single electroweak force at very high energy levels. In conditions such as those created inside particle accelerators, these two force sources become indistinguishable, revealing their shared origin and pointing to a more fundamental symmetry in nature. Building on this insight, theoretical physicists proposed grand unification theories, which suggest that at even higher energy levels, the strong nuclear force might also merge with the electro-weak force into a single, all-encompassing fundamental interaction. Although elegant and compelling, these theories still await experimental confirmation and remain an active area of research. The ultimate prize in this pursuit is the unification of all four forces, including gravity, into a comprehensive theory that would explain the behavior of everything in the universe, from the very smallest particles to the largest cosmic structures. Gravity's stubborn resistance to integration with quantum mechanics has made this a notoriously difficult challenge. One promising avenue of research is string theory, which proposes that all fundamental particles are manifestations of tiny vibrating strings at scales far smaller than atoms. This approach suggests that the forces we observe arise from different vibrational patterns of these strings, offering a tantalizing glimpse into a unified description of reality. Experimental efforts, such as high-energy particle collisions in large accelerators, seek to uncover evidence supporting these theories by revealing new particles or interactions that could unlock the secrets of force unification. In the earliest moments after the Big Bang, the universe was a seething, incomprehensibly hot and dense environment where all fundamental forces were unified into one. As the cosmos expanded and cooled, these forces gradually separated, giving rise to the distinct interactions we observe today. Among them, the weak nuclear force emerged as essential for processes involving subatomic particles like neutrinos and phenomena such as beta decay. Imagine the newborn universe as a rapidly cooling broth of particles. The weak nuclear force played a critical role in the formation of the first atomic nuclei, guiding the combination of quarks into protons and neutrons as temperatures dropped. These nucleons then became the foundation for atoms, setting the stage for the formation of matter as we know it. The saga of the universe's origin and evolution is a complex interplay of forces, particles, and cosmic events. It is a story of continuous discovery, where each new insight brings us closer to understanding the profound mechanisms that govern existence itself, from the infinitesimal to the infinite. However, the weak nuclear force plays an indispensable role in the subtle but critical reactions that govern the transformation between neutrons and protons, a process that profoundly influences the elemental composition of the universe. In the primordial moments following the Big Bang, as a seething, high-energy soup of particles churned and collided, neutrons and protons continuously interacted under the influence of this weak force. This fundamental interaction enabled some neutrons to convert into protons by emitting elusive particles called neutrinos. These transformations were far from trivial. They established the vital ratio between protons and neutrons in the early universe, a ratio that dictated the path of cosmic chemical evolution. This delicate balance was the cornerstone of nucleosynthesis, the era roughly a few minutes after the Big Bang when the first atomic nuclei began to form. Without the weak nuclear force facilitating the conversion of neutrons into protons, the primordial mix would have skewed, resulting in a drastically different distribution of elements. The process led to the formation of hydrogen and helium, the simplest and most abundant elements that still dominate the cosmos today. These two elements laid the groundwork for everything that followed: stars, planets, and eventually life itself. The weak nuclear force, in this way, was the silent architect behind the elemental foundation of the universe. Its subtle but crucial influence shaped the very chemical landscape of existence, reminding us of the profound interconnectedness of the fundamental forces that govern reality. On the other end of the nuclear spectrum, The strong nuclear force operates with astonishing power and precision, holding atomic nuclei together against forces that would otherwise tear them apart. Imagine the atomic nucleus as an ultra-dense cluster of protons and neutrons, collectively known as nucleons. Protons, each carrying a positive electric charge, naturally repel one another due to electromagnetic forces, much like two magnets pushing against each other when aligned with like poles. However, this repulsion alone cannot explain the observed stability of atomic nuclei. Enter the strong nuclear force, an extraordinarily powerful interaction that works over minuscule distances, roughly the size of an atomic nucleus itself. It acts as a formidable glue, binding protons and neutrons tightly together to overcome the electromagnetic repulsion between the positively charged protons. This force is fundamentally stronger than electromagnetism, but operates only within a very short range, ensuring that its influence is confined precisely to the nuclear scale. The mechanism behind this force involves the exchange of particles known as gluons, which mediate the interaction between quarks, the even smaller constituents of protons and neutrons. When nucleons are sufficiently close, gluons enable the strong nuclear force to act, creating a stable bond that holds the nucleus intact. This force not only explains why atomic nuclei can exist, but also why they remain stable despite the protons' natural tendency to repel each other. Nevertheless, this balance is precarious. In very large nuclei containing many protons, the repulsive electromagnetic forces can overwhelm the strong nuclear force. When this happens, the nucleus becomes unstable, leading to radioactive decay, a natural process by which unstable atoms transform into more stable forms. Thus, the strong nuclear force not only enables the formation of stable atomic nuclei, but also sets fundamental limits on the size and composition of atoms, influencing the very nature of matter around us. Shifting focus from the realm of the atomic nucleus to the vast expanse of the cosmos, the distinction between ordinary matter and dark matter reveals one of the greatest mysteries in modern astrophysics. Ordinary matter, which makes up stars, planets, and everything visible, is composed of atoms and molecules. This familiar matter interacts with electromagnetic forces, which allow it to emit, absorb, and reflect light. These light interactions provide the basis for most of our observations of the universe, through telescopes, satellites, and various instruments. Dark matter, in stark contrast, remains invisible and elusive. It does not interact with light or any form of electromagnetic radiation, rendering it undetectable through conventional means. Unlike ordinary matter, dark matter is believed to be made of exotic particles that have yet to be identified within the known particle physics framework. Its existence is inferred solely through its gravitational effects on visible matter and the structure of the universe itself. One of the most striking differences between ordinary and dark matter lies in how each responds to gravity. Ordinary matter tends to clump together under gravitational attraction, forming stars, galaxies, and planetary systems. Dark matter, however, forms an unseen vast scaffold that pervades the cosmos. It exerts gravitational forces that influence the motion of galaxies, the distribution of ordinary matter, and the large-scale structure of the universe. This invisible framework shapes the formation, shape, and movement of the visible cosmos. The importance of dark matter cannot be overstated. Observations of galaxies reveal that they rotate at speeds that should cause them to fly apart if only ordinary matter were present. The gravitational pull from visible matter alone is insufficient to hold these galaxies together at such high rotation speeds. Dark matter's gravitational influence explains this anomaly, holding galaxies intact and ensuring their stability over cosmic time. Despite the fact that we cannot directly observe dark matter, its gravitational fingerprints are unmistakable. It accounts for a significant portion of the total mass in the universe, profoundly influencing cosmic evolution and structure formation. The ongoing quest to understand the nature of dark matter captivates scientists and astronomers, pushing the boundaries of particle physics and cosmology. Through indirect observations and theoretical models, researchers strive to uncover the properties of these mysterious particles that silently shape the universe we inhabit. The evidence for dark matter is compelling and multifaceted. One of the most telling observations comes from studying the rotation curves of galaxies. Stars located at the outer edges of spiral galaxies move at surprisingly high speeds that defy expectations based solely on the visible mass within those galaxies. According to classical gravitational theory, the stars farther from the galactic center should orbit more slowly as the gravitational pull weakens with distance. However, measurements consistently show that these stars maintain unexpectedly rapid velocities. This puzzling behavior can only be explained if there is additional mass exerting gravitational influence, mass that cannot be accounted for by visible matter alone. This unseen mass, attributed to dark matter, acts like an invisible halo surrounding galaxies, providing the necessary gravitational glue to keep the stars bound to their cosmic homes. Without this dark matter scaffold, galaxies would not hold together as we observe them today. In summary, the weak and strong nuclear forces operate at the smallest scales, orchestrating the fundamental processes that govern atomic stability and elemental formation, while dark matter dominates the large-scale structure of the universe, guiding the formation and behavior of galaxies through its mysterious gravitational presence. Together, these forces and phenomena highlight the extraordinary complexity and interconnectedness of the cosmos, from the subatomic realm to the vast stretches of intergalactic space, illustrating a universe governed by unseen interactions that shape everything we see and experience. However, they do not indicate the presence of sufficient visible matter alone to account for the gravitational forces observed in many cosmic phenomena. This discrepancy points to the existence of an additional unseen form of mass commonly referred to as dark matter. Dark matter is believed to provide the essential gravitational pull necessary to keep outer stars in their rapid orbits around galaxies, preventing them from drifting away into the void of space. One of the most significant pieces of evidence supporting the existence of dark matter emerges from observations of galaxy clusters. When scientists study the motions of individual galaxies within these clusters, they find that the total mass calculated solely from visible galaxies falls dramatically short of what is needed to keep the cluster gravitationally bound. The galaxies move with such velocity that the gravitational force exerted by the observable matter alone could not hold them together. This suggests that there is far more mass present, hidden from view and not emitting any form of detectable light. Similarly, the phenomenon known as gravitational lensing provides additional clues. This effect occurs when light traveling from distant celestial objects bends around massive galaxy clusters, much like how a glass lens refracts light. The bending of light reveals the presence of mass that is exerting gravitational influence, mass that exceeds what can be accounted for by visible matter alone. By carefully studying these distortions in light, scientists are able to map the distribution of dark matter within and around these clusters, highlighting its pervasive influence across cosmic structures. Furthermore, the cosmic microwave background radiation that is the remnant glow from the earliest moments of the universe, contains subtle fluctuations that carry vital information about dark matter. These variations in the background radiation reveal how matter was distributed shortly after the Big Bang and provide indirect evidence of dark matter's influence on the formation of large-scale structures such as galaxies and clusters. This radiation acts like a cosmic fingerprint, illustrating the unseen scaffolding dark matter provides throughout the cosmos. Taken together, these diverse lines of evidence weave a compelling narrative. Dark matter fills crucial gaps in our understanding of the universe's mass and structure. It is a hidden yet essential component of the universe, accounting for a significant portion of its total mass while remaining invisible to all forms of electromagnetic observation. Detecting dark matter is an enormous challenge, akin to searching for a shadow without a clear outline or source. Scientists believe that dark matter constitutes approximately 85% of the total matter in the universe, yet it does not emit, absorb, or reflect light, making it completely undetectable by conventional optical instruments. Instead, researchers must rely on the gravitational effects dark matter exerts on visible matter, radiation, and the overall structure of the universe to infer its presence. Just as a planet's gravity influences the orbits of moons and nearby objects, the gravitational pull of dark matter shapes the movement of stars, galaxies, and clusters. One of the primary observational methods involves studying the rotation speeds of galaxies. Galaxies spin at such astonishingly high speeds that if they were composed solely of visible matter, stars at their outer edges would be flung off into space. Yet, these stars remain firmly bound within their galaxies, indicating the presence of an unseen mass believed to be dark matter that provides the necessary gravitational glue. Another critical observational technique is gravitational lensing, where the path of light from distant galaxies and quasars is bent around massive objects like galaxy clusters. This bending occurs because the combined gravitational influence of both visible and dark matter warps the fabric of spacetime. By analyzing these lensing effects, scientists can reconstruct maps of dark matter distribution and gain insight into its properties and abundance. However, despite these indirect clues, many challenges remain. Dark matter does not interact with ordinary matter through electromagnetic forces, meaning it neither emits nor scatters light, radio waves, or any other form of electromagnetic radiation. This invisibility complicates attempts at direct detection in laboratory settings. Many experiments worldwide are dedicated to detecting dark matter particles, often hypothesized to be weakly interacting massive particles, or WIMPs, which interact so feebly with normal matter that they leave only the faintest of signals, if any at all. The vastness of space itself compounds these challenges. The immense distances, the complex interplay of forces, and the faintness of signals demand highly sensitive instruments and prolonged observation times. Theoretical models of dark matter vary significantly, each predicting different properties, interactions, and effects. This diversity of models leads to multiple interpretations of observational data and necessitates persistent creative approaches coupled with advanced technology to narrow down the possibilities. Investigating dark matter is a monumental scientific pursuit, a cosmic detective story unfolding at the frontiers of knowledge. Researchers inch forward, piecing together fragments of evidence, testing theories, and developing new tools to understand this elusive substance. Their quest is daunting, but fueled by the promise that unlocking the secrets of dark matter will illuminate some of the most profound mysteries about the origin, composition, and fate of the universe. Among the many theories seeking to explain dark matter, the cold dark matter theory stands out as a leading candidate. This theory proposes that dark matter is composed of slow-moving particles that formed shortly after the Big Bang. These particles would have gravitationally clumped together over billions of years, serving as the cosmic scaffolding for the large-scale structures we observe today, such as galaxies and galaxy clusters. Their weak interaction with ordinary matter explains why they remain undetected by electromagnetic means, but exert a gravitational pull strong enough to bind cosmic structures. Another significant hypothesis is warm dark matter, which suggests that dark matter consists of particles moving slightly faster than those proposed by the cold dark matter theory. These particles would still exert substantial gravitational forces, but could influence the development of cosmic structures differently, potentially accounting for certain observations that cold dark matter does not fully explain. Alternatively, some scientists propose modified gravity theories as an explanation, questioning whether our current understanding of gravity is complete. Instead of invoking unseen particles, these theories suggest alterations to gravitational laws themselves that might account for the phenomena attributed to dark matter, such as the unexpected rotational speeds of galaxies and the gravitational binding of galaxy clusters. More exotic ideas have also been proposed, including supersymmetry, a theoretical framework suggesting that every known particle has a heavier, undiscovered partner. These heavier partner particles could potentially compose dark matter, adding a profound new dimension to particle physics and cosmology. Similarly, some theories consider primordial black holes, massive objects formed in the earliest moments after the Big Bang, as candidates for dark matter. These black holes, if they exist in sufficient numbers, could explain gravitational effects without requiring new particle types. As the scientific community continues to explore these theories, they constantly test predictions against observations from telescopes, particle detectors, and cosmic surveys. Each new discovery refines our understanding and occasionally challenges existing paradigms, driving the evolution of cosmological thought. Understanding dark matter promises to revolutionize our comprehension of the universe's origins and evolution. It holds the key to fundamental insights about the forces that shape the cosmos and the processes that led from a hot, dense early state to the vast, richly structured universe we observe today. Dark matter, though invisible and undetectable by conventional means, exerts a profound gravitational influence that molds the formation of galaxies and clusters. Imagine the universe as a vast fabric stretched across space and time. Dark matter creates the underlying framework of this cosmic tapestry, guiding how ordinary matter aggregates to form stars, planets, and galaxies. By delving deeper into the nature of dark matter, researchers hope to uncover the conditions and processes that prevailed shortly after the Big Bang. The interactions of dark matter likely played a crucial role in cooling the early universe, enabling the ignition of the first stars and the emergence of cosmic structure. This ongoing exploration paints a detailed picture of cosmic evolution, illustrating how the universe transitioned from an incredibly hot and dense primordial state into the complex, beautiful cosmos we inhabit today. Through relentless observation, innovative experiments, and theoretical ingenuity, humanity gradually unravels the mysteries of dark matter, bringing us closer to understanding the fundamental nature of reality itself. Moreover, the quest to unveil the elusive properties of dark matter holds the promise of illuminating some of the most profound mysteries governing the vast cosmos. If scientists succeed in identifying the precise particles or phenomena that constitute dark matter, this breakthrough could revolutionize our understanding of the universe's grand architecture. It would provide fresh perspectives on how the universe itself expands over time, how galaxies come into existence and evolve through billions of years, and perhaps even reveal the ultimate cosmic fate awaiting all matter and energy. Grasping the role that dark matter plays is not merely a matter of filling gaps in existing cosmological models. It invites us to embark on a deeper exploration into the fundamental building blocks of existence itself. Such discoveries have the potential to rewrite entire chapters of cosmic history, reshaping our understanding of everything, from the tiniest particles to the vast expanses stretching across space and time. Within this context, string theory emerges as a fascinating and profoundly insightful framework, offering a radically different perspective on the universe's inception. Rather than viewing the universe's fundamental components as point-like particles, string theory suggests that the basic constituents of all matter and forces are instead incredibly tiny, vibrating strings. Picture these strings as infinitesimal strands of spaghetti, each one vibrating in unique patterns. The specific manner in which each string vibrates determines the properties of particles, such as their mass, charge, and other essential attributes. When applied to the earliest moments of the universe, string theory proposes a comprehensive framework that could unify all fundamental forces of nature, including the notoriously difficult to integrate force of gravity. Understanding these forces as interconnected is crucial for deciphering the conditions present at the very beginning of time during the event commonly referred to as the Big Bang. Traditional theories of physics have struggled to reconcile gravity with quantum mechanics, but string theory offers promising pathways to bridge this divide. It posits that at extremely high energies and densities, those theorized to exist at the universe's birth, the interactions between these vibrating strings could explain phenomena that have otherwise remained elusive. Furthermore, string theory hints at the existence of multiple dimensions beyond the 3 dimensions of space and 1 dimension of time that we experience in everyday life. These additional dimensions, hidden from our direct perception, could have existed before the universe itself began in the way we conventionally understand it. The presence of such higher dimensions allows for different dynamics that might have preceded the Big Bang. This opens the door to a variety of fascinating scenarios for the universe's origin, where interactions among strings in these multidimensional spaces could trigger the rapid expansion we now observe. While string theory remains largely theoretical, with many aspects still unproven through experimental data, it acts as a powerful tool in modern physics. It pushes the boundaries of human understanding about the universe's beginnings and challenges us to conceptualize the cosmos in innovative ways. By striving to uncover the fundamental nature of reality, string theory compels us to rethink everything, from the smallest quantum particles to the vast fabric of space-time itself. Expanding on these cosmic questions, multiverse theories offer another captivating viewpoint on the origins of our universe. These theories propose that our universe might be just one among countless other universes, each with its own unique conditions, physical laws, and cosmic histories. This idea arises from the recognition that the initial conditions of our universe, including its temperature, density, and structural layout, appear to be remarkably fine-tuned to allow for the emergence of life, the formation of galaxies, and the existence of complex matter. Within the framework of the multiverse, our universe can be imagined as a single bubble floating in an immense cosmic foam. Each bubble universe could have arisen through different processes, producing a vast array of physical laws and fundamental forces. For example, in some universes, the forces governing matter might operate differently, drastically altering how stars, planets, and galaxies form and evolve. In others, the conditions might be so extreme or foreign that familiar matter as we know it could not exist, resulting in realms completely alien to any human experience or comprehension. One particularly influential theory within this broader multiverse context is the idea of cosmic inflation. This theory suggests that immediately after the Big Bang, the universe underwent an extraordinarily rapid expansion, so rapid that it smoothed out any irregularities in the early cosmos. This inflationary phase could explain why the universe today appears so uniform and isotropic on large scales, while still allowing for the complex structures we observe, such as galaxy clusters and cosmic filaments. The concept of cosmic inflation also supports the multiverse hypothesis by implying that this rapid expansion might not have been a singular event. Instead, it could have generated a vast landscape of bubble universes, each budding off into its own spacetime with distinct properties. In this view, the multiverse is a dynamic, ever-expanding collection of universes, each governed by a different set of initial conditions and physical laws. Our universe is thus just one island in an infinite ocean of cosmic possibilities. Together, the investigations into dark matter, the theoretical advancements in string theory, and the far-reaching implications of multiverse theories compose an intricate tapestry of modern cosmology. They highlight humanity's relentless pursuit to comprehend the nature of existence and the origins of everything we observe. These ideas challenge our fundamental assumptions, urging us to explore realms far beyond the visible stars and galaxies, into dimensions and realities that test the limits of imagination and scientific inquiry. As scientists continue to probe deeper, utilizing advanced instruments, sophisticated mathematical models, and innovative experimental techniques, the coming decades may reveal answers to questions that have haunted humanity for centuries. What exactly is dark matter, and how does it shape the universe? How do vibrating strings unify the forces of nature and illuminate the dawn of time? Are we truly living in a singular universe, or is our reality one of many in an endless multiverse? Each step forward promises to enrich our understanding of the cosmos, bringing us closer to unraveling the grand narrative of existence itself. However, inflation might not unfold uniformly across the vast expanse of the multiverse. Instead, it could produce distinct bubbles of space-time, each bubbling with its own unique conditions and outcomes. This uneven process might explain the incredible variety we could expect to find within other universes, revealing regions where life not only exists but flourishes in unimaginable ways. Far from being a lone, isolated singularity with a fixed set of physical laws and parameters, our universe could be just one member in an enormous family of universes, each with different properties shaped by chance or underlying principles. This broader perspective challenges us to think beyond the confines of our own cosmic neighborhood. The special characteristics we observe in our universe, from the fundamental constants to the forces governing matter and energy, might simply be one of many possibilities scattered across the multiverse. Each bubble's initial conditions could arise from random fluctuations during the earliest moments of cosmic inflation, or perhaps be the consequence of deep, unknown mechanisms buried in the fabric of reality itself. As a result, our understanding of existence expands from a single narrative into a grander, richer tapestry that embraces multiple realities. Among the most profound mysteries intertwined with these ideas is the nature of dark energy, an enigmatic force believed to be responsible for the universe's accelerating expansion. Despite decades of research, dark energy remains elusive, its exact character still beyond our grasp. To conceptualize dark energy, imagine the universe as a balloon that is continuously being inflated. As the balloon grows larger, every point on its surface moves further apart, symbolizing the galaxies receding from one another over time. This analogy helps illustrate the observable fact that cosmic expansion is speeding up rather than slowing down, as one might intuitively expect from gravity alone. One influential explanation suggests that dark energy is actually a property inherent to space itself. According to this idea, as space stretches and expands, it generates more dark energy, which in turn fuels further expansion. This concept is rooted in the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. Just as adding air causes a balloon to expand uniformly, the cosmological constant represents a constant energy density permeating all of space, pushing the universe apart evenly. This explanation fits neatly into the mathematical framework of modern physics, yet leaves unanswered the question of why the cosmological constant has the value we observe. Another intriguing hypothesis involves the notion of dynamic fields, sometimes called quintessence. Unlike the cosmological constant, which remains fixed, quintessence envisions a type of energy that can change over time, somewhat like the varying flow of a river rather than a steady stream. This dynamic energy density could cause the rate of the universe's expansion to speed up or slow down at different epochs, adding complexity to the cosmic story. Imagine a river whose currents ebb and flow, sometimes rushing rapidly and other times meandering gently. Quintessence introduces a similar fluidity to the force driving cosmic expansion. Beyond these ideas, some scientists propose that our understanding of gravity itself may require revision on the largest scales. In Einstein's general relativity, gravity is often depicted as the curvature of spacetime, a flexible fabric that bends in response to mass and energy. However, it is conceivable that this fabric behaves differently when stretched over enormous cosmic distances. Alternative gravity models suggest that modifications to Einstein's equations could explain the accelerating expansion without the need to invoke dark energy at all. This line of thinking challenges the foundation of physics, proposing that the force governing the cosmos might have hidden complexities yet to be uncovered. Despite the allure of these theories, none have yet been definitively confirmed. Researchers continue to gather and analyze data from a variety of sources, such as distant supernovae, whose light reveals the rate of expansion billions of years ago, the cosmic microwave background, which encodes information from the universe's infancy, and the large-scale structure of galaxies spread across the sky. Each piece of evidence holds potential clues that could unlock the secrets of dark energy, shedding light on how our universe grows and changes over time. As we probe deeper into the cosmic depths, dark energy might eventually reveal properties and behaviors that challenge our current understanding, transforming how we perceive the universe and its destiny. Another profound frontier in modern physics is the quest for a theory of quantum gravity, which seeks to unite the two towering pillars of 20th century physics: quantum mechanics and general relativity. Quantum mechanics governs the subatomic world of particles and forces, describing nature at its tiniest scales with remarkable precision. General relativity, in contrast, explains the large-scale structure of the cosmos and the gravitational interaction between massive bodies. Reconciling these two frameworks into a single, coherent theory is essential for understanding the universe's earliest moments, a period still shrouded in mystery and beyond the reach of classical physics. Consider the Big Bang, the event marking the universe's origin. In its initial instance, the cosmos was unimaginably hot and dense, conditions so extreme that the smooth, continuous fabric of space-time described by general relativity breaks down. Quantum gravity theories propose that at these smallest scales, space and time might not be continuous at all, but instead composed of discrete, tiny building blocks. Instead of a fluid, flowing fabric, space-time could be granular and chaotic, resembling a turbulent foam more than a smooth sheet. By applying quantum principles to gravity, scientists hope to model these earliest conditions more accurately. These theories predict that space-time itself could fluctuate wildly, with quantum uncertainty making the very geometry of the universe unpredictable. In such a tempestuous landscape, the usual concepts of cause and effect might dissolve, and familiar physical laws may no longer hold. This radical environment could have profound consequences for how the universe evolved, influencing the distribution of matter and energy on cosmic scales. Quantum fluctuations during this primordial epoch may have seeded the variations that eventually grew into galaxies, stars, and planets. Tiny random differences in the density of matter could have been amplified by cosmic expansion, setting the stage for the complex structures we observe today. Thus, the chaotic quantum realm at the dawn of time may hold the key to understanding not just how the universe began, but why it took the form it did. As we explore these ideas, from uneven cosmic inflation to the mysterious push of dark energy and the granular fabric of space-time, our view of the cosmos becomes ever richer and more nuanced. The journey toward comprehending these profound mysteries continues to inspire and challenge humanity's quest for knowledge, promising to reshape our fundamental understanding of existence itself. Furthermore, quantum gravity holds the promise to profoundly deepen our understanding of the universe's earliest moments, shedding light on how the cosmos transformed from an unimaginably hot and dense primordial state into the cooler, structured expanse we witness today. By applying quantum principles to simulate conditions from the universe's infancy, researchers aim to unravel the complex processes that govern the formation of elementary particles, the emergence of fundamental forces, and the gradual shaping of the fabric of space-time itself. This line of inquiry not only offers a vivid glimpse into the universe's birth, but also opens pathways toward uncovering the foundational laws that govern phenomena as diverse as black holes, the cosmic web of galaxies, and perhaps even the very architecture of reality. The quest to unify quantum mechanics and general relativity is one of the most crucial endeavors in contemporary physics because these two pillars describe nature at vastly different scales. Quantum mechanics governs the subatomic realm, where particles behave in probabilistic and often counterintuitive ways, revealing a universe ruled by uncertainty and strange interactions. General relativity, on the other hand, excels at explaining how gravity orchestrates the motion of massive objects, such as planets and galaxies, by curving space-time itself. Yet, when confronted with extreme cosmic environments, such as the singularities inside black holes or the first fractions of a second after the Big Bang, the principles of quantum mechanics and general relativity clash, each failing to fully describe what happens under such extraordinary conditions. At the heart of a black hole, for instance, gravitational forces become so intense that they warp space-time to an extreme degree, while particles exist simultaneously on an infinitesimal quantum scale. Neither quantum mechanics nor general relativity alone can offer a complete picture of these realms. The current theoretical frameworks work exceptionally well in their respective domains, but falter when pushed to their overlapping boundaries. A unified theory that reconciles quantum phenomena with gravitational forces could unlock profound insights into the inner workings of the universe, revealing how the fundamental forces interact at a deeper level and addressing some of the most existential questions humanity faces. What was the origin of the universe? What constitutes dark matter and dark energy? How will the cosmos ultimately evolve? Bridging the gap between quantum behavior and gravity would not only help explain existing astronomical observations, but could also predict new phenomena yet to be discovered. Such a unifying framework would propel science closer to a comprehensive understanding of the cosmos, enhancing our grasp of the very fabric of reality. History shows that groundbreaking discoveries often arise from such paradigm shifts, transforming our worldview and inspiring new avenues of inquiry. For centuries, humanity's understanding of the cosmos has evolved dramatically. One of the most transformative milestones was the development of the Big Bang theory. This model proposes that the universe originated from a state of extreme heat and density roughly 14 billion years ago and has been expanding ever since. This concept revolutionized our perception of cosmic evolution, transforming a previously static and eternal view of the universe into a dynamic and evolving narrative with a defined beginning. A powerful piece of evidence supporting the Big Bang theory came from the discovery of the cosmic microwave background radiation. This faint, nearly uniform glow permeates all of space and represents the residual heat left over from the early universe, shortly after its formation. Analyzing this radiation allows scientists to peer back in time and reconstruct the conditions that prevailed mere moments after the cosmos began to unfold. On a more granular scale, the identification of fundamental particles has equally reshaped our understanding of matter. Scientists learned that everything surrounding us is composed of atoms, which themselves consist of smaller constituents: protons, neutrons, and electrons. This realization led to the development of the Standard Model of Particle Physics, a comprehensive framework explaining how these particles interact via four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. The discovery of quarks, which make up protons and neutrons, revealed an even deeper subatomic structure. These insights have allowed physicists to explore not just the composition of ordinary matter, but also the dynamic interactions occurring in extreme environments like those recreated in particle accelerators. These machines simulate conditions akin to those in the earliest moments of the universe, allowing scientists to observe how fundamental particles behave under high energy and intense forces. Adding further complexity to this cosmic puzzle are the discoveries of dark matter and dark energy. Unlike ordinary matter, which constitutes only a small fraction of the universe's total mass, dark matter makes up a substantial portion and influences how galaxies form, cluster, and move through space. Meanwhile, dark energy, a mysterious force driving the accelerated expansion of the universe, challenges scientists to rethink existing models of cosmic evolution and destiny. These enigmatic components highlight how much remains unknown, fueling ongoing research and debate. Each discovery, from the smallest particle to the grandest galactic structure, has expanded our comprehension of the universe while simultaneously raising new questions and revealing deeper mysteries. These advances continue to refine our understanding of the cosmos and its underlying principles. The evolution of scientific thought has dramatically shifted humanity's perspective on the universe's origin and nature, moving away from ancient philosophical and religious interpretations toward empirical evidence and testable theories. Historically, many civilizations believed in a static, eternal universe with Earth or humanity at its center, a geocentric model where celestial bodies revolved around a stationary Earth. This worldview dominated for centuries until the advent of more precise observational tools. The invention of the telescope marked a turning point. Astronomers like Galileo Galilei discovered moons orbiting Jupiter, directly challenging the geocentric model by demonstrating that not everything revolved around Earth. This opened the door to a broader, more complex understanding of the cosmos. In the 20th century, observations by Edwin Hubble radically transformed cosmology. By measuring the redshifts of distant galaxies, Hubble showed that the universe is expanding, implying that it was once smaller, denser, and hotter. This discovery lent robust support to the Big Bang theory and shifted scientific consensus toward a dynamic, evolving cosmos. Technological advancements and theoretical progress have since provided further evidence for cosmic phenomena like the cosmic microwave background radiation. This relic radiation serves as a tangible imprint of the early universe's heat, bolstering the Big Bang model and encouraging a view of the cosmos as a constantly changing and unfolding entity rather than a static backdrop. Through these interconnected discoveries and evolving theories, humanity's understanding of the universe has moved from simple Earth-centered models to a vast, dynamic, and mysterious expanse governed by fundamental laws that scientists continue to probe. The ongoing quest to unify the laws of the very small with those of the very large promises to unlock even deeper secrets, enriching our knowledge of the universe's origins, composition, and ultimate fate. Moreover, Concepts such as dark matter and dark energy have emerged as fundamental elements that have profoundly reshaped our understanding of the cosmos. These enigmatic components account for a substantial portion of the universe's total mass and energy content, yet their true nature remains elusive and deeply mysterious. Their existence challenges scientists to rethink the very fabric of reality itself. As our tools for exploring the cosmos become increasingly advanced, with sophisticated telescopes and interstellar probes venturing farther into space, our hypotheses and theoretical models about the origin and structure of the universe continue to evolve. Each new discovery forces us to reevaluate not only the mechanics of the cosmos, but also humanity's place within it, broadening the scope of our cosmic understanding and moving us away from traditional narratives steeped in mythology and philosophy toward a framework grounded firmly in scientific inquiry. Throughout the history of human thought, a series of pivotal figures and landmark projects have shaped our comprehension of the universe and its intricate evolution. One of the earliest major contributors to this endeavor was the ancient Greek philosopher Aristotle. His observations and theories about the heavens laid foundational groundwork for the systematic study of celestial phenomena. Though Aristotle's ideas were eventually challenged and refined, his work established important precedents for the astronomical inquiries that followed, helping to cultivate a tradition of curiosity and rational investigation that persists today. Advancing several centuries forward, the revolutionary contributions of Nicolaus Copernicus marked a significant paradigm shift in our cosmic perspective. By proposing a heliocentric model that placed the sun, not the Earth, at the center of our solar system, Copernicus fundamentally altered humanity's self-image and its conceptualization of the cosmos. This dramatic shift set in motion a chain of scientific progress that questioned long-held assumptions and encouraged new ways of thinking. Building upon Copernicus's groundbreaking model, Johannes Kepler developed his famous laws of planetary motion. By mathematically describing how planets orbit the sun in elliptical paths, Kepler provided a far more accurate and predictive framework for understanding planetary dynamics. This precision was crucial for the advancement of astronomy and laid the groundwork for later discoveries. Galileo Galilei's contributions cannot be overstated, particularly in terms of technological innovation and observational evidence. By enhancing telescopic technology, Galileo was the first to observe celestial bodies with unprecedented clarity. His discoveries of Jupiter's moons and the phases of Venus delivered compelling evidence that supported the heliocentric model and challenged the dominant geocentric views of the time. Galileo's work ignited a fervent enthusiasm for empirical, observation-driven science, cementing the scientific method as a cornerstone of inquiry. The 20th century witnessed yet another transformative leap with Albert Einstein's theories of relativity. Einstein revolutionized our understanding of space, time, and gravity by demonstrating how massive objects warp the fabric of space-time. His insights explained phenomena such as the bending of light around massive celestial bodies, fundamentally altering our comprehension of cosmic interactions. These theories not only deepened scientific knowledge, but also laid the intellectual foundation for modern cosmology. Subsequent projects like the Hubble Space Telescope, launched in the early 1990s, have expanded our cosmic horizons even further. Hubble's breathtaking images of distant galaxies, nebulae, and the large-scale structure of the universe have revealed critical insights about the expansion of the cosmos and provided evidence for the mysterious force known as dark energy. Such discoveries have been essential in piecing together the universe's vast and complex history, enabling scientists to form a more cohesive narrative of cosmic evolution. The discovery of cosmic microwave background radiation by missions such as the Cosmic Background Explorer, COBE, and later the Planck satellite provided a glimpse into the universe's infancy. This faint afterglow, a remnant of the Big Bang, serves as a snapshot of the universe when it was only a few 100,000 years old, offering critical evidence about how the cosmos has changed and expanded over billions of years. In addition to these historical milestones, INSCAD's cutting-edge collaborations like the Laser Interferometer Gravitational Wave Observatory LIGO have opened new frontiers by detecting gravitational waves, ripples in space-time produced by colossal events such as colliding black holes. These observations grant scientists remarkable insights not only into the universe's past, but also into the very fabric of reality itself, expanding our understanding of phenomena previously thought to be beyond reach. Together, these monumental figures and projects serve as vital milestones, each peeling back another layer of cosmic mystery. They reveal not only the origins of the universe, but also provide the foundation upon which future explorers will build as humanity continues its grand pursuit of knowledge. International collaborations have become indispensable in this quest, recognizing that the scale and complexity of the cosmos exceed the capabilities of any single nation. The universe operates on scales that defy national boundaries, compelling scientists from diverse countries to unite, sharing resources, expertise, and cutting-edge technology. This global pooling of knowledge significantly enhances the capacity to tackle complex cosmic questions that no individual country could address alone. Constructing high-powered telescopes and sophisticated spacecraft requires substantial financial investment and specialized skills. Through international partnerships, researchers combine their funds and expertise, enabling the development of instruments that are vastly more powerful and capable of capturing data that could unlock the universe's deepest secrets, from the formation of galaxies to the elusive nature of dark matter. Moreover, international collaborations foster a rich diversity of perspectives and methodologies. Scientists contribute unique approaches shaped by their distinct cultural backgrounds and educational traditions, spurring innovative breakthroughs. When scientific communities converge across borders, it creates fertile ground for the exchange of theories and techniques, enriching the collective understanding of cosmic phenomena. The benefits extend beyond science, promoting diplomacy and fostering cooperation between nations. Shared scientific projects build a sense of common purpose, uniting countries in their pursuit of exploration and understanding. The International Space Station exemplifies this spirit, serving not only as a platform for scientific research, but also as a powerful symbol of global teamwork. Astronauts from various countries live and work together aboard the station, advancing space science and technology while forging bonds that transcend geopolitical differences. Recent technological advancements have dramatically transformed our ability to peer deeper into the cosmos. Next-generation telescopes outfitted with state-of-the-art sensors and enhanced imaging capabilities now provide astronomers with clearer and more detailed views of distant galaxies and cosmic phenomena than ever before. This improved vision allows scientists to study the early universe in unprecedented detail, unraveling how galaxies formed, evolved, and interacted over billions of years. The ability to capture light from the faintest and most distant sources has opened new windows onto the universe's earliest epochs, revealing not just static images, but dynamic processes shaping cosmic history. These advancements continue to refine our models of cosmic origins and evolution, challenging us to reconsider what we know and pushing the boundaries of human knowledge further outward into the vastness of space and time. Additionally, the emergence of space-based observatories has revolutionized our capacity to explore the cosmos by completely removing the distortions caused by Earth's atmosphere, which often interfere with observations made from the ground. Instruments positioned beyond the confines of our atmosphere have the extraordinary ability to detect a vast range of electromagnetic radiation, including infrared and ultraviolet wavelengths, which are typically blocked or scattered before reaching terrestrial telescopes. This capability enables scientists to examine celestial bodies and phenomena that would otherwise remain concealed, providing unprecedented glimpses into the universe's most secretive stages, such as the moments immediately following the Big Bang and the intricate processes that led to the birth of the very first stars. In parallel with these advancements, the creation of gravitational wave detectors marks a monumental breakthrough in astronomy and physics. These highly sensitive instruments can perceive subtle ripples in the fabric of space and time generated by colossal cosmic events, including the collisions and mergers of black holes. Observing these gravitational waves offers scientists new perspectives on the historical narrative of the universe, illuminating the environmental conditions that fostered black hole formation and shedding light on the dynamic evolution of these enigmatic objects. The detection of gravitational waves opens a fresh window into realms previously accessible only through theoretical speculation, allowing us to probe the universe in fundamentally novel ways. Moreover, the rapid progression in computational power, combined with innovative data analysis methods, has empowered astronomers and astrophysicists to handle and interpret enormous volumes of data with far greater efficiency and precision. Employing sophisticated algorithms and cutting-edge artificial intelligence techniques, researchers can meticulously sift through vast cosmic datasets to detect patterns, irregularities, and phenomena that would be virtually impossible to uncover through manual examination alone. This computational prowess enables the extraction of deeper insights from the colossal amount of information gathered by modern observatories and space missions, gradually constructing a more comprehensive and intricate portrait of the cosmos and humanity's position within it. Every new revelation in this ever-expanding field brings us incrementally closer to unraveling the profound mysteries surrounding the origins of the universe and the intricate processes underpinning our very existence, revealing an awe-inspiring complexity that makes the quest for cosmic knowledge one of the most captivating and enduring endeavors of humankind. Computer-generated simulations hold a crucial and transformative role in enhancing our understanding of the early universe and Earth's own cosmic history by allowing scientists to virtually recreate the extreme conditions prevailing shortly after the Big Bang. Imagine attempting to solve an immensely complicated puzzle where numerous pieces are missing or obscured. Within the realm of cosmology, these simulations serve as a vital framework to fill in these gaps. The nascent universe existed in an incredibly hot, dense, and turbulent state where energy and matter were in relentless, chaotic flux. By leveraging the computational might of powerful supercomputers, researchers can model the complex interactions between fundamental particles and forces that govern that volatile epoch. These virtual experiments simulate essential cosmic phenomena such as the formation and evolution of large-scale structures, the distribution and clustering of galaxies, and the elusive behavior of dark matter, components of the universe that elude direct observational detection through telescopes. Within these meticulously constructed digital environments, scientists input a multitude of physical principles rooted in our current understanding of particle physics, gravitation, thermodynamics, and radiation. The simulations track the motion and interactions of particles over time, generating a dynamic, evolving cosmic landscape where the interplay of gravity, temperature fluctuations, and electromagnetic radiation collectively shape the universe's developmental trajectory. Through this process, the simulations produce a detailed timeline of the universe's evolution, charting the transformation from its blazing, primordial beginnings into the cooler, more organized cosmos that we observe today. Crucially, the outcomes of these computational models can be juxtaposed against actual observational data collected from telescopes and space-based instruments. This comparative analysis allows scientists to refine and adjust theoretical frameworks, improving their fidelity and predictive power. When a simulation yields a cosmic structure or galaxy distribution that closely aligns with what astronomers observe in the night sky, it bolsters confidence in the underlying physics and the assumptions embedded within the model. Ultimately, computer simulations serve as a sophisticated virtual laboratory for cosmologists and astrophysicists, enabling them to experiment with a variety of hypothetical scenarios, examine the influence of different physical factors, and develop a more nuanced, layered understanding of the processes that have shaped our vast universe. This exploration is akin to reading a complex narrative written in the very fabric of space and time, uncovering the intricate story of cosmic origins, evolution, and the forces at play across billions of years. Recent technological strides have dramatically transformed the ways in which scientists visualize and comprehend cosmic events. Historically, astronomers relied predominantly on optical telescopes to capture and study light emitted from distant celestial bodies across various wavelengths. Today, the integration of advanced imaging technologies combined with the immense processing power of modern computers allows the creation of extraordinarily detailed visual representations of cosmic phenomena, many of which were once confined to theoretical conjecture. Among the most thrilling advancements is the field of gravitational wave astronomy. When two massive bodies such as black holes engage in a spiraling dance that culminates in their violent merger, they generate faint but detectable ripples propagating through the fabric of space and time. Sophisticated detectors positioned around the world are now capable of capturing these subtle signals, transforming abstract data into tangible visual formats. These graphical interpretations grant us the extraordinary ability to witness cosmic events that transpired billions of light years away, effectively bringing the distant universe closer to our senses. Another remarkable leap forward involves computer simulations designed to model dramatic cosmic phenomena. Harnessing the immense computational capabilities of supercomputers, scientists recreate cataclysmic events like supernova explosions and the gradual assembly of galaxies, applying intricate physics equations to forecast the behavior of matter under the most extreme conditions imaginable. These virtual reconstructions provide vivid illustrations of processes unfolding over millions or even billions of years, condensed into brief, comprehensible sequences. The resulting imagery and animations not only captivate the imagination with their stunning visualizations, but also deepen our understanding of the fundamental mechanics governing the universe's structure and evolution. Through these digital windows into the cosmos, we gain invaluable insights into the majestic and often violent forces that have shaped the vast cosmic landscape we inhabit. Moreover, the advent of multi-messenger astronomy has revolutionized the way scientists visualize and understand the cosmos, vastly expanding our ability to perceive the universe beyond what was once imaginable. This innovative approach integrates diverse streams of information gathered from multiple cosmic messengers. Instead of relying solely on traditional electromagnetic signals such as the light emitted by a supernova, multi-messenger astronomy combines data from gravitational waves, ripples in the fabric of space-time generated by cataclysmic cosmic events, and neutrinos, those elusive, nearly massless particles produced in vast quantities during high-energy phenomena like exploding stars and merging black holes. By synthesizing information from these fundamentally different sources, researchers are able to assemble a far richer, more nuanced picture of cosmic events, weaving together narratives that tell a profound story of the universe's dynamic processes. This synthesis of data from varied messengers allows scientists to peer into the depths of the cosmos in unprecedented ways. Space-based observatories, notably the Hubble Space Telescope and the James Webb Space Telescope, have dramatically sharpened the clarity and depth of the images we capture from distant realms. These powerful instruments extend our vision deeper into space and time than ever before, unveiling intricate details of galaxies, stars, and planets that remained hidden until recently. Their capability to image across a broad range of wavelengths, spanning from the cool, penetrating infrared to the energetic ultraviolet, unlocks a spectrum of information inaccessible to the naked eye or ground-based telescopes. This multifaceted view reveals different facets of cosmic structures, shedding light on their composition, behavior, and evolution with remarkable precision. The transformation in visualization is profound. What once were simple snapshots of celestial objects have evolved into elaborate explorations, rich in complexity and layered meaning. These advancements have enabled humanity to experience the grandeur of the cosmos in immersive ways that stimulate curiosity, wonder, and deep scientific inquiry. Astrophotography in particular has played a pivotal role in this shift, becoming not just a tool for capturing stunning images, but a gateway to discovering phenomena that remain invisible to ordinary vision. Advanced imaging technologies extend our reach across the electromagnetic spectrum, revealing dust and gas clouds that cloak stars and galaxies. These features, invisible in visible light alone, are critical to understanding how cosmic structures form and change over time, serving as signposts of ongoing processes in the universe's vast evolutionary tapestry. The discoveries fueled by these technological strides have challenged and refined long-standing theories about the formation and growth of galaxies. Deep sky surveys have uncovered immense populations of distant galaxies dating back to the universe's formative epochs, providing direct glimpses into the processes of galactic merging and growth that span billions of years. Observing these ancient structures enables scientists to reconstruct the dynamic history of cosmic evolution, revealing the intricate dance of matter that shapes the universe. Additionally, the ability to capture high-resolution images of transient cosmic events, such as supernova explosions and the birth of new stars within stellar nurseries, offers a window into the life cycle of stars and the elemental processes underpinning the chemical enrichment of the cosmos. When a massive star reaches the end of its life and explodes, it disperses heavy elements essential for planet formation and ultimately for life itself. Each image encapsulates a fleeting moment in this grand narrative, illustrating the delicate interplay of creation and destruction that propels cosmic evolution forward. Beyond the scientific community, astrophotography wields immense power in engaging the public imagination and fostering a collective sense of wonder. The breathtaking images captured by modern telescopes inspire emotional connections to the universe, sparking curiosity and motivating people worldwide to explore and learn more about the cosmos. This growing public fascination drives increased support for space exploration and research, prompting scientists to pursue deeper questions about the mysterious components of the universe, such as dark matter and dark energy, as well as the fundamental nature of space-time. Thus, astrophotography does more than beautify our understanding of the cosmos. It actively shapes the trajectory of scientific inquiry, providing vivid, tangible evidence that helps to crystallize abstract theories into comprehensible, awe-inspiring realities. In parallel, three-dimensional imaging technologies have transformed the study of the universe's most fundamental building blocks, the particles that make up matter itself. Traditional two-dimensional images, while informative, often fall short in conveying the complex spatial relationships and dynamic interactions between particles. By harnessing advanced techniques such as electron tomography, scientists can now create detailed three-dimensional reconstructions of particles at the nanoscale, revealing entire assemblies and molecular complexes in stunning detail. This enhanced spatial perspective allows researchers to visualize how particles cluster, bond, and influence one another, shedding light on the forces, such as electromagnetic interactions that govern their formation and behavior. Moreover, three-dimensional imaging captures particle dynamics over time, enabling the study of processes like crystal growth or phase transitions with newfound clarity. This dynamic view is critical for understanding how matter organizes itself under varying conditions, thereby advancing fields such as materials science, nanotechnology, and biochemistry. The implications of these breakthroughs extend far beyond laboratory research. By providing a comprehensive visual framework, three-dimensional imaging facilitates innovations that depend on the precise control and manipulation of matter at the smallest scales. This progress paves the way for new technologies and materials, with applications ranging from medicine to electronics, highlighting the deep interconnectedness between visualization techniques and practical scientific advancements. Visualization plays a central role in bridging the gap between complex scientific concepts and broader public understanding. Abstract ideas that might otherwise feel intangible become accessible through compelling graphics, animations, and images, which serve as cognitive anchors for comprehension. Imagine the difficulty of grasping the vastness of outer space or the intricate dance of subatomic particles without visual aids. Through visualization, concepts such as galaxy formation or behavior of electrons around an atomic nucleus become vivid sensory experiences. Patterns and trends in scientific data emerge more clearly when rendered graphically, enabling audiences to discern relationships and draw conclusions with greater ease than text-based explanations alone can provide. For example, a simple graph illustrating the progression of climate change over time can reveal subtle shifts and dramatic trends that raw numbers fail to communicate effectively. This visual storytelling evokes emotional responses and fosters a deeper connection with the subject matter, making the science more relatable and urgent. In this way, visualization not only enhances our understanding, but also cultivates empathy and motivation to engage with critical scientific issues, driving a more informed and connected society. The evolution of visualization in astronomy, particle physics, and beyond demonstrates the profound power of seeing to know. From the sweeping vistas captured by space telescopes to the intricate three-dimensional maps of particle interactions, visualization is an indispensable tool that transforms data into discovery and curiosity into comprehension. It invites us to explore the universe with fresh eyes, expanding the boundaries of human knowledge and imagination. Furthermore, interactive visual tools have revolutionized the way people engage with scientific concepts by enabling individuals to explore complex principles at their own pace, resulting in a much deeper and more personal understanding. This hands-on, immersive experience transforms what might otherwise be passive absorption of information into an active and dynamic learning process. It encourages a natural curiosity, urging users to ask questions, experiment with ideas, and delve further into scientific phenomena on their own terms. The power of visualization goes beyond simply clarifying difficult concepts. It also democratizes science itself, breaking down barriers that have historically made scientific knowledge feel exclusive or intimidating. Whether someone is a seasoned researcher working at the cutting edge of their field, or a high school student encountering these ideas for the first time, visual aids help science become less of an abstract, distant discipline confined to the sterile environment of laboratories, and more of a vivid, engaging narrative that invites participation from all walks of life. At the heart of scientific inquiry lies one of the most profound and awe-inspiring mysteries known to humanity: the origin of the universe. Central to this enigma is the Big Bang Theory, a framework that suggests the entire cosmos began as an incredibly hot, dense point, roughly 13,800,000,000 years ago. Despite decades of research and remarkable advances in astrophysics, many critical questions about this event remain unanswered. One of the most perplexing mysteries is the cause of the Big Bang itself. While scientists have developed detailed models describing the rapid expansion that followed, the precise event or process that caused this initial singularity, the infinitely small and dense state from which everything emerged, is still unknown. Unlocking the nature of this initial trigger could revolutionize our understanding of reality, potentially revealing new dimensions of physics or aspects of the universe that challenge our current theories. Another major puzzle that continues to captivate researchers concerns dark matter and dark energy. Observations suggest that these mysterious substances make up most of the universe's total mass energy content. Dark matter, though invisible and undetectable by emitted light, exerts a significant gravitational pull that holds galaxies together and shapes cosmic structures on a grand scale. It interacts with normal matter in ways that defy our expectations, appearing almost ghost-like in its behavior. Dark energy, on the other hand, is believed to be responsible for driving the accelerated expansion of the universe, pushing galaxies farther apart at an ever-increasing speed. Identifying the true nature of dark matter and dark energy is essential to understanding not only how the universe formed, but also how it will continue to evolve over billions of years. In addition to these mysteries, scientists are deeply engaged in exploring the theory of cosmic inflation. This hypothesis posits that in the very first moments after the Big Bang, the universe underwent a brief but extraordinarily rapid expansion. Cosmic inflation helps explain why the universe appears so uniform and isotropic when observed at large scales, yet the underlying physical mechanisms and triggers behind this inflationary phase remain elusive. Researchers strive to uncover what forces or conditions could have caused such a dramatic and sudden growth spurt in the fabric of space-time. Further complicating the cosmic picture is the intriguing possibility of a multiverse, a concept that suggests our universe might be just one among countless others, each governed by its own unique set of physical laws and constants. This idea pushes the boundaries of human comprehension and raises profound philosophical and scientific questions about the very nature of existence. What would it mean for reality if countless universes coexist alongside ours, some possibly with entirely different dimensions, particles, or even forms of life? The implications of the multiverse challenge our assumptions about what is fundamental or universal. Another fundamental question concerns the initial conditions of the universe itself. How did the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, and the elementary particles come together in such a precise, finely tuned way that allowed the cosmos to evolve into the rich and complex structure we observe today? This inquiry touches on the origins of physical laws. Are they inherent properties woven into the fabric of the universe from the very beginning, or did they emerge progressively as the universe expanded and cooled? These questions are at the frontier of cosmology and theoretical physics, driving scientists to develop new theories that may one day provide answers. As researchers continue to investigate these extraordinary questions, their work not only seeks to unravel the origins of the universe, but also aims to illuminate the very essence of reality itself. This quest makes the mysteries surrounding cosmic beginnings some of the most pivotal and inspiring challenges in human knowledge. Simultaneously, breakthroughs in technology are fundamentally transforming our ability to explore and understand the cosmos. Imagine standing at the shore of an immense, boundless ocean, where only now are we constructing the ships capable of venturing far into its uncharted depths. Advanced telescopes with unparalleled sensitivity enable astronomers to observe distant star systems and galaxies that were once beyond the reach of human instruments. These cutting-edge devices can detect light that has traveled billions of years through space and time, allowing scientists to glimpse the birth of stars and the evolution of galaxies across cosmic history. Such observations continually reshape our understanding, revealing complexities and phenomena that challenge previously held beliefs. Moreover, innovations in space travel technology are poised to extend humanity's reach well beyond the familiar confines of our solar system. Consider spacecraft that might use solar sails propelled purely by sunlight, or harness nuclear propulsion methods to dramatically reduce travel times between planets. These futuristic modes of travel bring the prospect of exploring neighboring planets, moons, and other celestial bodies closer to reality. Some of these destinations may harbor signs of life, or possess unique environments that could offer insights into planetary formation, habitability, and even the origins of life itself. Artificial intelligence plays an increasingly critical role in this exploration. By processing vast quantities of data collected from numerous space missions at speeds far exceeding human capability, AI can detect subtle patterns, anomalies, and correlations that would otherwise go unnoticed. This computational power accelerates scientific discovery by directing researchers to new areas of interest and providing insights that guide experimental and observational strategies. For example, AI could help identify the specific conditions conducive to the formation of exoplanets, planets orbiting stars outside our solar system, thereby expanding our understanding of where life might exist beyond Earth. In this rapidly advancing era, the intersection of technology and scientific inquiry not only deepens our knowledge of the cosmos, but also fuels humanity's enduring fascination with the universe. Each breakthrough brings us closer to answering the timeless questions about our origins, our place in the vast cosmic tapestry, and the ultimate fate of everything that exists. Furthermore, the field of material science is undergoing remarkable advancements that are revolutionizing our capacity to explore space. These developments are enabling the creation of materials that are not only significantly stronger, but also remarkably lighter than their predecessors. This combination of strength and lightness is crucial because the harsh environment of space demands materials capable of withstanding extreme temperatures, intense radiation, micrometeorite impacts, and prolonged exposure to the vacuum of space. With these new materials, engineers and scientists can design and build habitats, spacecraft components, and tools that are more durable, efficient, and reliable, ensuring the safety and success of future missions. The implications of these materials extend far beyond mere equipment improvements. They pave the way for establishing sustainable living environments beyond Earth. This could mean constructing self-sufficient habitats on the Moon, Mars, or even further afield, where astronauts can live and work for extended periods. The ability to fabricate lightweight yet robust structures reduces launch costs and enables larger, more complex modules to be transported and assembled in space. This advancement is essential for missions aiming at long-term human presence beyond our planet, contributing to humanity's broader aspiration to become a multiplanetary species. These technological breakthroughs are not isolated. Instead, they form a sophisticated, interconnected web of innovation that propels space exploration forward. Each new development feeds into the next, creating a dynamic synergy that multiplies the overall impact. For example, improvements in material science enhance spacecraft design, which in turn allows for more powerful scientific instruments, enabling deeper observations and data collection. This cyclical enhancement accelerates progress and opens new horizons in our quest to understand the cosmos. Looking to the future, the landscape of space exploration shines with promise and excitement. It is rich with opportunities for groundbreaking discoveries that have the potential to fundamentally reshape our understanding of the universe and our place within it. The pursuit of knowledge about the origins of the cosmos, the birth of galaxies, stars, and planetary systems, and the fundamental forces at play lies at the heart of several high-profile projects currently underway. One of the most eagerly awaited endeavors is the James Webb Space Telescope, an extraordinary observatory designed to peer back in time to the universe's earliest epochs. This telescope is optimized to detect infrared light, which allows it to see through clouds of cosmic dust and gas that obscure many celestial objects from view in visible light. By capturing the faint infrared signals from some of the first galaxies and stars formed shortly after the Big Bang, it promises to shed light on the processes that shaped the universe nearly 14 billion years ago. Its powerful instruments will help astronomers study the formation and evolution of these primordial objects in unprecedented detail. Alongside the James Webb Space Telescope, the European Space Agency's Euclid mission represents another ambitious project. This satellite is dedicated to mapping the geometry of the dark universe, a term that encapsulates the enigmatic dark matter and dark energy that dominate the cosmos but remain largely mysterious. By surveying millions of galaxies, Euclid aims to unravel how the universe's expansion has accelerated over time and to provide vital clues about the nature of dark energy, which is driving this acceleration. This mission's data will be crucial in understanding how cosmic structures evolved from the earliest times to the present day. Complementing these space-based observatories is the extremely large telescope, a next-generation ground-based facility that will dramatically enhance our ability to observe distant celestial phenomena. With a mirror diameter far surpassing previous telescopes, it will achieve unprecedented resolution and sensitivity, allowing astronomers to analyze the light from some of the universe's earliest galaxies. This telescope promises to provide new insights into cosmic evolution, from the formation of the first stars to the growth of massive galaxies over billions of years. Further expanding our observational capabilities is the planned Lunar Gateway, a space station designed to orbit the Moon. This platform will serve as a hub for scientific instruments and research projects that benefit from operating outside Earth's atmosphere, but within relatively close proximity to our planet. By offering a stable base for deep space observations and experiments, the Lunar Gateway will play a vital role in expanding humanity's reach into the cosmos and supporting future missions to the Moon, Mars, and beyond. Together, these pioneering initiatives form a comprehensive approach to exploring the universe's origins and its fundamental nature. They promise to unlock answers to profound questions about how galaxies, stars, and the very elements essential for life came into existence. Each project, whether space-based or ground-based, contributes unique data and perspectives that collectively deepen our understanding of cosmic history. Scientists driving these endeavors approach the grand question of the universe's origin by first establishing a clear set of research priorities. They begin by identifying the key mysteries that must be unraveled, such as the composition of the universe, its evolutionary trajectory, and the physical laws governing its behavior. This systematic approach helps organize the vast array of questions into manageable focus areas. One of the most challenging puzzles is the nature of dark matter and dark energy, which together account for the vast majority of the universe's content, but remain elusive in terms of direct detection and full comprehension. Dark matter, while invisible because it does not emit or absorb light, exerts gravitational forces that shape the motion of galaxies and large-scale structures. Dark energy, on the other hand, is responsible for the accelerating expansion of the universe, a discovery that won the Nobel Prize in Physics. Understanding these mysterious components is a top priority because they hold the key to how the cosmos has evolved and may influence its ultimate fate. Research efforts are inherently collaborative, involving multiple institutions, countries, and disciplines. This international cooperation pools expertise, resources, and technology, allowing for more ambitious projects such as launching advanced telescopes, performing particle physics experiments, or running complex computer simulations that recreate the conditions of the early universe. Collaboration enables the scientific community to tackle problems of increasing scale and complexity. Technological advances play a crucial role in shaping research directions. The invention of more sensitive and precise instruments continually pushes the boundaries of what can be observed and measured. These improvements often reveal unexpected phenomena, opening new questions and research avenues. For example, advances in detector technology might enable scientists to identify particles that make up dark matter, while new observational methods could measure subtle cosmic signals previously undetectable. Funding and resource allocation also influence the priorities and timing of research initiatives. Projects that align with broader scientific goals or capture public imagination tend to receive more financial support, guiding focus towards specific domains like cosmology, astrophysics, or particle physics. This dynamic environment ensures that research adapts and evolves as new discoveries are made and fresh insights emerge. As scientists delve deeper into dark matter and dark energy, several promising breakthroughs loom on the horizon. Dark matter is believed to constitute a substantial fraction of the universe's total mass, yet it does not interact with electromagnetic radiation, making it invisible through conventional telescopes. Its presence is inferred from gravitational effects on visible matter, such as the rotation of galaxies and the behavior of galaxy clusters. To detect dark matter directly, researchers are developing advanced detectors and experiments designed to identify the elusive particles theorized to compose it. Success in this area could revolutionize our understanding of the cosmos, revealing a fundamental component of reality previously hidden from view. Dark energy, in contrast, drives the universe's accelerating expansion, a phenomenon observed through distant supernovae and the distribution of galaxies across space and time. While its effects are measurable, its precise nature remains one of the greatest mysteries in modern cosmology. Upcoming telescopes and observational programs aim to study distant cosmic events with unprecedented accuracy, seeking data that might illuminate dark energy's properties. Alongside these observational efforts, theoretical physicists work on developing models that integrate dark energy and dark matter into a unified theoretical framework. Such breakthroughs could fundamentally alter how we conceptualize the universe, potentially revealing whether these entities are separate phenomena or manifestations of a deeper underlying reality. Beyond particles and forces, the universe can also be understood through the lens of harmonic frequencies and cosmic sound waves, offering a novel perspective on its intricate structure. Picture the universe as a vast, resonating system where every celestial object contributes to a cosmic symphony of vibrations. These vibrations manifest in phenomena such as gravitational waves, ripples in spacetime generated by cataclysmic events like black hole collisions, and pulsars, which are rapidly rotating neutron stars emitting rhythmic pulses of radiation. By studying these harmonic frequencies, scientists gain invaluable insights into the fundamental nature of matter, energy, and spacetime itself. Harmonic frequencies arise from the interaction of different cosmic elements and conditions, creating specific tones that serve as indicators of various materials or physical states in the universe. Detecting and analyzing these cosmic sounds helps researchers map the universe's composition and evolution, revealing hidden aspects of its structure and behavior. This approach complements traditional observations and deepens our understanding of the cosmos as a dynamic, interconnected system. Altogether, these multifaceted research efforts combine observational data, theoretical innovation, technological advancement, and international collaboration to push the boundaries of human knowledge. As we continue to explore the cosmos, we stand at the brink of profound discoveries that may transform our understanding of existence, illuminating the universe's origin, its current state, and its ultimate destiny. This relentless pursuit of knowledge reflects humanity's enduring curiosity and determination to uncover the deepest mysteries of reality itself.